Warp drives. The concept has captivated our imagination for decades, bringing the dream of faster-than-light travel into popular culture. But what is a warp drive really? And could it ever become more than just science fiction? In popular media, especially shows like Star Trek, warp drives allow spaceships to travel vast distances almost instantly. This idea has inspired generations, but the real-world science behind it is far more complex and mysterious. Faster-than-light travel is not just a matter of speeding up a spacecraft. According to Einstein's theory of relativity, as an object approaches the speed of light, its mass increases exponentially. This means that traveling at or faster than the speed of light requires an enormous amount of energy, far more than we can currently produce. Warp drives, however, offer a theoretical loophole. Instead of moving a ship through space at light speed, a warp drive would manipulate space itself. By compressing space in front of the ship and expanding it behind, the ship could move faster than light without technically breaking the speed limit. The most famous theoretical model for a warp drive comes from physicist Miguel Alcubierre. In 1994, he proposed a method for creating a warp bubble around a spaceship, allowing it to travel faster than light. This model, while groundbreaking, presented its own set of challenges, chief among them being the energy requirements. To generate a warp bubble, Alcubierre's model suggests you would need a form of exotic matter with negative energy. This kind of matter doesn't exist naturally on Earth and remains one of the biggest obstacles to making warp drives a reality. Even if we could find exotic matter, the amount of energy required to create a warp bubble would be astronomical. Early estimates suggest we would need more energy than is produced by the entire planet. But recent advancements have started to chip away at this daunting figure. There are small steps being taken toward understanding and testing warp drive concepts in the real world. NASA's EagleWorks lab, led by Harold "Sonny" White, has been exploring the physics of warp drives. Their experiments aim to figure out if it's possible to generate the conditions necessary for a warp bubble, even on a small scale. This kind of research is still in its infancy, but it's opening doors to new possibilities. With more research, funding, and time, we might begin to make real progress toward faster-than-light travel. But for now, the dream of warp drives remains on the far edges of scientific possibility. In the following sections, we'll break down the science, explore the hurdles, and look at how close, or far, we are from achieving what was once thought impossible. Faster-than-light travel, or FTL, is the idea of moving through space faster than the speed of light. According to modern physics, this is currently impossible, because the speed of light is considered the ultimate limit in the universe. The issue lies in the laws of relativity. Einstein's theory tells us that as an object approaches the speed of light, its mass increases. The closer you get to light speed, the more energy is required to keep accelerating, eventually becoming infinite at the speed of light itself. This means that no matter how powerful your engines are, reaching or exceeding light speed would demand more energy than we can ever produce. Even the most advanced technologies we have today fall dramatically short of what's needed for FTL travel. This doesn't stop scientists from exploring other options. Instead of focusing on moving through space at the speed of light, the concept of warping space offers a workaround. In this way, space itself can expand and contract, making it possible to traverse vast distances much more quickly. The idea is that, by manipulating space-time, a ship wouldn't need to break the speed of light. Instead, it would ride a wave of space that bends around it. This would allow the ship to reach distant stars without violating the laws of relativity. In essence, the ship itself wouldn't be moving faster than light within its bubble. Instead, the space around it is being reshaped, allowing it to travel faster than light in a cosmic sense. But this concept, while fascinating, still faces immense theoretical and practical challenges. The amount of energy required to warp space in this way is staggering. Early models suggest that you'd need more energy than exists in all the known universe just to move a small ship a short distance. This makes faster-than-light travel seem far beyond our reach, at least for now. However, some scientists believe there might be ways to reduce the energy demands. Tweaking the models and finding new sources of energy could, in theory, lower the requirements enough to make FTL travel possible. But these remain distant ideas, far from anything we could implement today. Another issue is the nature of space-time itself. While we know it can bend and stretch, Doing so in a controlled way is beyond our current technological capabilities. We lack both the understanding and the tools to manipulate space on the necessary scale. There's also the problem of stability. Even if a warp bubble could be created, keeping it stable over time is a whole other challenge. If the bubble collapsed prematurely, it could destroy anything inside it, making this type of travel incredibly dangerous. And then there's the matter of navigation. Traveling faster than light through warped space would require a completely new approach to piloting a spacecraft. The distances and forces involved would be unlike anything humans have ever experienced, raising questions about how we could safely control such a journey. So while the concept of faster-than-light travel is theoretically intriguing, it remains one of the most difficult challenges in modern physics. Scientists continue to explore new ideas, but we are still a long way from turning FTL travel into reality. Einstein's theory of relativity is the foundation for understanding why faster-than-light travel is so difficult. The theory consists of two main parts: special relativity and general relativity, both of which shape our understanding of space, time, and motion. Special relativity focuses on how objects behave at high speeds, particularly near the speed of light. One of its key principles is that the speed of light is constant, no matter how fast you're moving. This constant speed sets a hard limit on how fast anything in the universe can travel. As objects move faster, time begins to behave differently for them. This is known as time dilation, where time actually slows down for objects approaching the speed of light. It's one of the strange consequences of special relativity that makes the idea of warp drive so compelling. In general relativity, Einstein expanded on his ideas to include gravity. He described gravity not as a force, but as a curvature in space-time caused by mass. Large objects like planets and stars bend the fabric of space-time, and this bending is what we perceive as gravity. This concept of curved space-time is crucial for understanding how a warp drive might work. Instead of trying to move an object faster than light through flat space, you could, in theory, manipulate the space-time around it. That's the idea behind creating a warp bubble. However, general relativity also imposes limits. Moving at or beyond the speed of light within normal space-time still seems impossible. Any attempt to do so would require infinite energy, which makes the warp drive a potential solution, but also a very complicated one. Einstein's equations show that mass and energy are directly related. As you accelerate toward the speed of light, the energy you need grows exponentially, and so does the object's mass. This is why nothing with mass can travel at light speed. It would take infinite energy to get there. The implications for faster-than-light travel are profound. Not only do we need to account for the energy requirements, but we also have to grapple with the way space and time themselves distort at high velocities. This is one of the many hurdles scientists face when exploring FTL possibilities. In fact, the theory allows for phenomena like wormholes, which could, in theory, enable shortcuts through space. But practical ways to create or use them remain theoretical at best. Relativity also gives us a new way to think about distances. When you travel close to the speed of light, space itself seems to shrink in the direction of motion. While this effect doesn't allow you to exceed the speed of light, it shows how space and time are more flexible than we once thought. One of the key insights of relativity is that space and time are interconnected. You can't change one without affecting the other. This is why any future warp drive or faster-than-light technology would need to consider both space and time as part of the equation. Einstein's theory of relativity redefined our understanding of the universe. It opened the door to new ways of thinking about space travel, but it also set limits that we're still trying to overcome. These limits continue to shape the debate around the possibility of warp drives and FTL travel. The space-time continuum is a concept that combines space and time into a single, four-dimensional framework. In simple terms, it means that space and time are not separate, independent entities, but rather intertwined. This union helps explain how objects move and interact in the universe. To visualize it, think of space-time as a fabric that can be stretched or bent by the presence of mass or energy. When something massive like a planet or a star exists in space-time, it creates a depression in this fabric, which we experience as gravity. The more massive the object, the deeper the bend. This bending of space-time is what causes objects to move toward one another. Smaller objects are essentially falling into the curves created by larger ones. This interaction between mass, space, and time is fundamental to understanding the nature of the universe. But it's not just space that's affected. Time also bends and warps in the presence of massive objects. This means that time can pass differently depending on where you are in space. The stronger the gravitational pull, the slower time moves. This warping of time is known as time dilation, and it's one of the stranger consequences of the space-time continuum. For example, clocks on a spaceship near a massive object, like a black hole, would tick more slowly compared to clocks far away from it. This has been proven with real experiments on Earth. In addition to gravity's impact on space and time, the space-time continuum allows for the concept of movement through 4 dimensions. We're familiar with the 3 spatial dimensions, length, width, and height, but time is considered the 4th dimension. Movement through time is constant for everyone, but the rate at which time passes can vary. This is why the idea of warping space-time is so exciting for things like faster-than-light travel. If we could bend space-time enough, we could theoretically create shortcuts through space, making it possible to travel huge distances in a much shorter time. Space-time can also be thought of as flexible, not rigid. While light travels in straight lines in normal space, a warp in space-time can bend that path just like light bending around a curved surface. This flexibility is key to understanding how phenomena like black holes and potential warp drives might work. Einstein's theory of relativity gave us a mathematical way to describe the space-time continuum. His equations show that the more massive an object, the more it warps space-time, leading to stronger gravitational effects and slower passage of time. This is why time moves differently depending on how close you are to a gravitational source. The space-time continuum isn't just a theoretical construct. It's been confirmed through a number of experiments. From GPS satellites adjusting their clocks to account for time dilation, to light bending around massive galaxies, we see evidence of space-time warping all around us. In terms of faster-than-light travel, manipulating the space-time continuum is seen as one of the only possible solutions. Instead of trying to outrun light, we would need to fold or compress space-time itself to reduce the distance between 2 points. This idea is central to the concept of warp drives. In the end, the space-time continuum isn't just about where you are in the universe, it's also about when. Space and time are inextricably linked, and understanding their relationship is essential if we ever hope to make faster-than-light travel a reality. One of the biggest challenges in making warp travel a reality is the immense energy it would require. According to current models, the energy needed to warp space-time would be astronomical. Early estimates suggested you'd need more energy than the entire universe produces just to move a small spacecraft. The energy demands stem from the idea of creating a warp bubble, a region of compressed and expanded space-time around the ship. To generate this bubble, you'd need a type of energy that's far beyond what we currently have access to. This is where the concept of negative energy comes into play. Negative energy isn't something we encounter in everyday life. It's a theoretical form of energy that would allow for the creation of the warp bubble without needing infinite energy. However, producing and controlling negative energy on a large scale is another major hurdle for warp technology. Even if we could harness negative energy, the amount required is still staggering. Some scientists have proposed methods to reduce these energy needs, like tweaking the shape of the warp bubble to make it more efficient. But even with these adjustments, the power needed would still be far beyond anything humanity can currently generate. Today, our most powerful energy sources, like nuclear reactors, can't come close to what's required for warp travel. To put it in perspective, you'd need the energy equivalent of several stars just to power a single warp drive. This makes the search for new, more powerful energy sources a priority for any future warp technology. One possibility is tapping into zero-point energy, a concept from quantum mechanics. Zero-point energy refers to the idea that even in a vacuum, space is never truly empty and contains a small amount of energy. If we could find a way to extract this energy, it might provide the power needed for warp drives. Another option is antimatter. Antimatter is the opposite of regular matter, and when the two collide, they release an enormous amount of energy. However, creating and storing enough antimatter to power a warp drive is a significant challenge, as we've only managed to produce tiny amounts in laboratories so far. Solar energy from stars, while abundant, isn't nearly concentrated enough to meet the needs of warp travel. Fusion energy, which powers stars, could be another potential solution, but we're still decades away from mastering controlled fusion here on Earth. Some scientists speculate that dark energy, the mysterious force causing the universe to expand, could be the key. Dark energy is believed to make up most of the universe's energy, but we know very little about it. If we could harness dark energy, it might unlock the ability to warp space-time. The scale of the energy required also raises questions about efficiency. Even if we could generate enough energy for a warp drive, sustaining that energy for the duration of a trip would be incredibly difficult. Finding ways to minimize energy consumption will be crucial if warp travel is ever to become practical. There's also the issue of how to convert that energy into usable form. Even with breakthroughs in energy production, the technology to direct and focus such immense power into creating a stable warp bubble doesn't exist yet. Developing that technology will be as important as finding new energy sources. At the heart of the energy problem is the fact that we're dealing with physics on a cosmic scale. Warping space-time isn't just a technological issue. It's about bending the very fabric of the universe, and that requires an understanding and control of energy far beyond our current capabilities. One of the primary theoretical constraints on faster-than-light travel comes from Einstein's theory of relativity. It states that as an object approaches the speed of light, its mass increases exponentially. This means that the energy required to keep accelerating grows without limit, making it impossible to reach or exceed light speed under normal circumstances. This exponential increase in mass creates a barrier for anything with mass trying to travel at light speed. Photons, which are massless particles, can move at the speed of light, but anything with mass would need infinite energy to achieve the same velocity. This fundamental limit has shaped the way we think about FTL travel. Another key issue is causality, which refers to the relationship between cause and effect. If faster-than-light travel were possible, it could lead to situations where effects occur before their causes, violating the laws of physics as we understand them. This could result in paradoxes, such as events happening out of order, which our current understanding of the universe doesn't allow. There's also the problem of time dilation. As an object moves closer to the speed of light, time slows down for the traveler relative to an observer at rest. If FTL travel were possible, time could behave in ways that challenge our fundamental understanding of how it flows. Space-time itself also poses a constraint. The faster you go, the more space-time distorts around you. This warping can create significant obstacles for navigation and stability, especially if you're moving faster than light. These distortions would be difficult to predict and control. Even if you could bypass the speed of light, you'd need to account for the immense distances between stars. Traveling at faster than light speeds doesn't erase the fact that the universe is vast, and the forces involved in crossing such distances could still create problems for any theoretical technology. Quantum mechanics introduces another layer of complexity. On the quantum level, particles can sometimes behave in ways that seem to violate relativity. However, these effects don't scale up to macroscopic objects, meaning that FTL travel for humans or spacecrafts isn't possible based on what we currently know about quantum theory. In addition to these physical constraints, there's the issue of energy conservation. The laws of thermodynamics dictate that energy in a closed system must be conserved. Faster-than-light travel might violate these principles, leading to questions about where the energy goes and how it affects the universe. Wormholes and other theoretical shortcuts through space-time offer possible workarounds to these constraints, but they come with their own issues. Wormholes, if they exist, would need to be stable and traversable, and we currently have no way to create or maintain them. Their instability could result in catastrophic collapse before any useful travel could take place. One of the most difficult constraints is simply the unknown. Our understanding of the universe is incomplete, and there may be laws of physics we haven't discovered yet that further restrict or even permit FTL travel. Until we uncover these deeper truths, we're limited by what we know. Another theoretical issue involves communication at faster-than-light speeds. Just as travel would challenge our understanding of physics, so would communication. Sending information faster than light could also result in paradoxes or violations of causality, creating additional theoretical barriers. In summary, the theoretical constraints on faster-than-light travel are deeply rooted in the laws of physics as we currently understand them. These limits are not just technological but fundamental, involving the very structure of space-time and the nature of the universe itself. In 1994, physicist Miguel Alcubierre introduced a groundbreaking idea that seemed to offer a solution to the problem of faster-than-light travel. He proposed a method that didn't require an object to move faster than light itself. Instead, his concept involved bending or warping space-time around the object. Alcubierre's idea was inspired by Einstein's general theory of relativity, which allows for the manipulation of space-time. In his model, a spacecraft would remain stationary within a bubble of flat space, while the space in front of it would contract and the space behind it would expand. This warp bubble would allow the ship to travel faster than light from an outside observer's perspective without actually breaking any physical laws. The key advantage of this model is that the ship would technically remain at rest within its bubble, avoiding the infinite energy problem associated with traditional FTL travel. Alcubierre's warp drive relies heavily on the idea of manipulating space-time, but it also comes with significant challenges. The most notable is the requirement for exotic matter, a hypothetical form of matter that has negative energy density. This type of matter is essential for creating and maintaining the warp bubble. Exotic matter, if it exists, could allow for the creation of negative energy, which is needed to make the space in front of the bubble contract. However, exotic matter has never been observed in nature, and its existence remains purely theoretical. The energy requirements for the Alcubierre drive are enormous. Early calculations suggested that the amount of energy needed to power a warp drive could exceed the total energy output of an entire star. This makes the concept fascinating but currently far from practical. Alcubierre's model also raised questions about stability. Even if a warp bubble could be generated, keeping it stable over time would be incredibly difficult. A collapsing warp bubble could have disastrous consequences for anything inside it, making safety another key concern. Another potential issue is the problem of inertia. Inside the bubble, the spacecraft wouldn't experience any movement, but once the bubble collapses, the sudden change in speed could have a devastating effect on the ship and its occupants. This raises questions about how to safely decelerate from faster-than-light speeds. Alcubierre's paper sparked a wave of interest in the possibility of FTL travel, and it continues to influence research today. However, despite its theoretical promise, the practical implementation of a warp drive remains elusive. The concept has inspired further exploration into the manipulation of space-time, but many challenges remain. Even with these hurdles, Alcubierre's work is significant because it offers a possible path forward. While the energy requirements and exotic matter needs are daunting, the idea that faster-than-light travel might not violate the laws of physics has opened new avenues of research. Some scientists are now looking for ways to reduce the energy requirements or find alternatives to exotic matter. While no breakthroughs have been made yet, Alcubierre's concept continues to fuel both imagination and scientific investigation. Alcubierre's 1994 paper may not have provided an immediate solution to faster-than-light travel, but it laid the foundation for a whole new way of thinking about space travel. It suggested that by working with the fabric of space-time itself rather than trying to move through it, we might one day unlock the secrets of faster-than-light travel. The idea behind the warp bubble is that instead of moving an object through space faster than light, space itself is manipulated around the object. The space in front of the object contracts, while the space behind it expands. This creates a sort of wave that the object can ride, allowing it to move faster than light relative to an outside observer. Inside the warp bubble, the spacecraft would remain stationary. This avoids the problem of needing infinite energy to accelerate the ship. The bubble moves through space, carrying the ship with it, without violating the speed of light within the bubble itself. What makes this concept possible, at least theoretically, is that it's not the object that's moving faster than light. It's space-time around it that's being manipulated. This warping of space doesn't violate any physical laws because space itself isn't bound by the same speed limits that apply to objects within it. The key challenge is creating and maintaining the bubble. To generate this effect, you would need a massive amount of energy, and it would have to be precisely controlled. The expansion and contraction of space-time must be perfectly balanced to keep the bubble stable. Exotic matter, with its negative energy, is critical for making this happen. It's the negative energy that allows space-time to be compressed in front of the bubble and expanded behind it. Without it, the warp bubble would collapse, and the faster-than-light travel would be impossible. Once the bubble is created, the ship inside would feel no acceleration. From the perspective of those inside the bubble, the ship wouldn't be moving at all. This is because the space within the bubble remains flat and unaffected by the warping occurring outside. Outside the bubble, however, things would look very different. To an external observer, the ship would be traveling at superluminal speeds. The distance between the ship and its destination would seem to shrink as the bubble moved through space. The nature of the bubble itself is fascinating. It essentially bends space-time in such a way that the ship can bypass the usual restrictions of light speed. The bubble acts as a kind of shield, protecting the ship from the effects of extreme speed. One major concern with the warp bubble is what happens when it reaches its destination. The sudden collapse of the bubble could release a huge amount of energy. Managing this safely would be a critical challenge for any practical application of warp technology. There's also the question of how to steer the bubble. In theory, the shape of the bubble could be adjusted to change direction. But manipulating space-time in such a precise way would require technology far beyond anything we have today. And another potential issue is the effect of the warp bubble on the space around it. The massive distortions in space-time could have unpredictable consequences, potentially damaging the environment through which the bubble travels. This raises concerns about the safety of using such a technology near planets or other celestial bodies. In essence, the warp bubble is a clever workaround to the limitations of faster-than-light travel. Instead of trying to force an object to break the speed of light, it manipulates the space around the object. But while the theory is elegant, turning it into reality remains a monumental task. The fundamental idea behind warp travel relies on the manipulation of space itself. To achieve faster-than-light travel, space in front of the warp bubble is compressed, while space behind it expands. This simultaneous action allows the bubble, and anything inside it, to move forward without breaking the speed of light within the local space. Compressing space in front of the bubble means that the distance between the spacecraft and its destination becomes smaller. It's like folding a piece of paper so that 2 points on it are much closer together. The bubble shortens the distance, making it possible to travel vast distances in a short amount of time. Behind the bubble, the opposite happens. Space expands, effectively pushing the bubble forward. This expansion creates a kind of propulsion, though it's not in the traditional sense of rockets or engines. The bubble moves because the space behind it is constantly stretching, driving the craft forward. This expansion and compression need to happen at exactly the right rate. Too much compression in front could cause the bubble to destabilize. Too little expansion behind would prevent the bubble from moving efficiently through space. One of the remarkable aspects of this concept is that the ship inside the bubble doesn't experience any of the extreme forces associated with acceleration. The bubble moves through space while the ship remains in a calm, stable environment. There's no need to worry about g-forces or time dilation inside the warp bubble. From the outside, however, the situation looks very different. The rapid compression and expansion of space could create visual distortions, potentially warping the light around the bubble. This could make the ship appear stretched or compressed to an observer watching from a distance. These space-time distortions also raise questions about what happens to objects or particles that might cross the path of the bubble. Would they be compressed or expanded along with the space around them? Could this create hazardous conditions for anything in the bubble's path? The process of compressing and expanding space requires an enormous amount of control. It's not just about bending space. It's about bending it in precisely the right way. Any miscalculations could cause the bubble to collapse, potentially releasing catastrophic amounts of energy. The energy required to maintain this balance is staggering. Current models suggest that the amount of energy needed would far exceed what's possible with today's technology. Without a new and sustainable source of energy, this method of travel remains purely theoretical. Another challenge is how to initiate and sustain the compression and expansion. We understand the basic principles in theory, but the technology to actually manipulate space-time on such a scale doesn't exist. Figuring out how to generate and maintain a warp bubble is a major hurdle that science has yet to overcome. The nature of the compression and expansion also means that the warp bubble itself is isolated from the rest of space. This could make communication with the outside world difficult, as signals would struggle to pass through the distorted space-time around the bubble. Despite these challenges, The concept of compressing and expanding space remains one of the most promising approaches to faster-than-light travel. It sidesteps the need to move a ship through space at impossible speeds and instead focuses on changing the space around it. But the practical implementation of such a concept is still far beyond our reach. The energy required to power an Alcubierre warp drive is one of the biggest obstacles to making it a reality. Early calculations suggested that the amount of energy needed would be immense, far beyond anything humanity could currently produce. In fact, some estimates indicated it would require more energy than what is contained in entire stars. This energy would be necessary to warp space-time, creating the bubble that allows faster-than-light travel. The key issue is that warping space on such a scale demands an incredible amount of negative energy or exotic matter, which we don't yet know how to produce in large quantities, if at all. The concept of negative energy is critical to the function of the warp drive. Negative energy is what allows space-time to contract in front of the bubble and expand behind it. Without it, the entire idea of the warp bubble falls apart, as normal positive energy wouldn't be enough to manipulate space this way. But even if we could harness negative energy, the sheer amount required is staggering. Some models have suggested that powering a warp drive to travel interstellar distances would need energy equivalent to the mass of Jupiter. These figures make it clear why the energy problem is so daunting. To reduce the energy requirements, some researchers have proposed adjusting the shape of the warp bubble. By making the bubble more efficient, the energy demands might be lessened. Still, even with these modifications, the energy needed remains far beyond what any technology today can generate. Another proposed solution is to harness energy from astronomical sources, such as harnessing the energy of stars or tapping into the theoretical zero-point energy of the quantum vacuum. While these ideas are intriguing, they remain speculative and are not anywhere near being practical. Antimatter has also been suggested as a potential energy source. When antimatter collides with matter, it releases massive amounts of energy, far more than chemical reactions like burning fuel. However, producing and storing enough antimatter to power a warp drive is currently beyond our capabilities. Fusion energy, which powers the sun, might be another option in the distant future. If we could perfect fusion technology, it could provide the kind of massive energy output required for something as demanding as a warp drive. But practical sustainable fusion is still a technology of the future. The energy requirements also raise questions about sustainability. Even if we could generate the necessary power, maintaining it for long-distance travel would be extremely difficult. The longer the journey, the more energy would be needed to keep the warp bubble stable. Another concern is how to direct and focus this energy to warp space-time in the precise way needed for the Alcubierre drive to function. We don't just need raw power. We need a method for controlling that power with incredible precision to ensure the stability of the warp bubble. While the energy barrier remains one of the biggest challenges to making the Alcubierre warp drive a reality, it's also an area where future breakthroughs could dramatically change the equation. Advances in energy production, storage, and control could one day make what seems impossible now more achievable. For now, the energy requirements for an Alcubierre warp drive remain in the realm of theoretical speculation. Without a major leap in our understanding of energy and space-time, faster-than-light travel will remain an exciting but distant possibility. Exotic matter is a term used to describe a type of matter that behaves very differently from the matter we encounter in our everyday lives. Unlike normal matter, which has positive mass and energy, exotic matter is theorized to have negative energy or negative mass. This unusual property is what makes it so important for theories like the Alcubierre warp drive. In physics, exotic matter is often associated with negative energy density. This negative energy is what allows space-time to bend in the unusual ways required for faster-than-light travel. It's crucial for creating the contraction and expansion of space that the warp drive relies on. The concept of exotic matter comes from the idea that certain theoretical particles or quantum states might have this negative energy. Some models in quantum field theory suggest that negative energy could exist, but it's never been observed in nature. So, while it's an intriguing idea, it remains hypothetical. One example of how exotic matter might work comes from the Casimir effect. This is a quantum phenomenon where two uncharged parallel plates in a vacuum experience a force that's attributed to negative energy between them. While this is a tiny effect, it hints at the possibility that negative energy might be real, at least in small amounts. However, the amount of exotic matter needed for a warp drive would be far greater than anything we've ever detected. To create a stable warp bubble, we would need an enormous quantity of negative energy. This is one of the biggest obstacles to developing faster-than-light travel technology. Another problem is that exotic matter with negative mass would behave very differently from normal matter. Instead of being attracted to other objects through gravity, it would repel them. This strange behavior could make it difficult to handle or contain, even if we were able to produce it. Despite the challenges, exotic matter remains an essential part of many advanced theoretical models in physics. It's not just important for warp drives, but also for other concepts like wormholes, which also require negative energy to remain stable. Without exotic matter, many of these ideas fall apart. Scientists are actively searching for ways to detect or create exotic matter. Some experiments in particle physics and quantum mechanics are looking for signs of negative energy or particles with unusual properties. But so far, nothing conclusive has been found. There's also the question of whether exotic matter could be artificially generated. Some researchers believe that advanced technologies, possibly involving quantum fields or high-energy physics, might one day be able to produce the negative energy needed for applications like warp drives. But this is purely speculative at the moment. Even if we could generate exotic matter, there would be significant challenges in storing and using it. Since it behaves so differently from normal matter, the technology to handle it safely doesn't exist. This adds another layer of complexity to the already difficult task of making warp travel possible. In addition to technical challenges, there are theoretical concerns about the existence of exotic matter. Some physicists argue that the laws of nature might prevent the creation of negative energy in the amounts required for warp travel. Others believe that if exotic matter does exist, it might have unpredictable or dangerous effects. For now, exotic matter remains a mystery. It's a theoretical solution to a theoretical problem, but its potential could be game-changing if we ever find a way to harness it. Without it, though, concepts like the warp drive will remain out of reach. Negative energy plays a crucial role in the theoretical construction of warp drives. It's the key ingredient that allows the manipulation of space-time, enabling the formation of a warp bubble around a spacecraft. Without negative energy, the contraction and expansion of space required for faster-than-light travel would be impossible. In the context of the Alcubierre warp drive, negative energy is needed to compress space in front of the bubble and expand it behind. This warping effect is what lets the ship move through space faster than light without breaking the laws of physics. Essentially, negative energy fuels the space-time distortions necessary for the warp drive to function. Negative energy isn't something we encounter in everyday physics. It's a theoretical concept that arises from quantum mechanics and general relativity. For a warp drive to be possible, large amounts of negative energy would need to be produced or discovered, and this remains one of the greatest challenges. The reason negative energy is so important is that it has the ability to curve space-time in ways that positive energy cannot. While positive energy leads to gravitational attraction, negative energy can create repulsive effects. This repulsion is what allows space-time to stretch and contract in a controlled way for faster-than-light travel. One of the few known phenomena that hints at the existence of negative energy is the Casimir effect. In this quantum effect, two plates placed extremely close to each other in a vacuum experience an attractive force due to negative energy between them. However, the amounts involved are minuscule compared to what would be needed for a warp drive. Even though negative energy seems theoretically possible, generating and controlling it at the necessary scale is beyond our current technological capabilities. The quantities needed for a warp bubble are astronomical, far exceeding what we can currently produce or harness. The exotic nature of negative energy also raises questions about how it interacts with normal matter. If we were able to generate it, could it be safely contained and manipulated? These are issues that would need to be resolved before any practical application of a warp drive could be realized. Another challenge is that negative energy is highly unstable. In theory, it could dissipate or decay rapidly, making it difficult to sustain over the long periods of time required for interstellar travel. This instability poses a major problem for creating a stable warp bubble. There are also concerns about the potential side effects of using negative energy. Some physicists speculate that large amounts of negative energy could have unpredictable consequences for the space-time continuum. It's possible that manipulating space-time on such a large scale could create dangerous distortions or even collapse regions of space. Negative energy doesn't just power the warp drive, it also helps protect the spacecraft from the extreme conditions of faster-than-light travel. By creating a bubble of flat space-time around the ship, negative energy prevents the ship from experiencing time dilation or harmful relativistic effects. The scarcity of negative energy in the universe, or at least our current inability to harness it, means that faster-than-light travel remains purely theoretical until we find a way to produce or access negative energy in usable quantities. The warp drive will remain an idea rather than a reality. Despite the immense challenges, negative energy remains a central focus for researchers exploring the possibility of faster. The Casimir effect is one of the few real-world phenomena that hints at the existence of negative energy. It occurs when two uncharged parallel plates are placed extremely close together in a vacuum. Even though the space between them is seemingly empty, quantum fluctuations cause a force to push the plates toward each other. These quantum fluctuations are essentially small, temporary changes in energy that occur even in a vacuum, where we would normally expect no matter or energy to exist. The Casimir effect arises because the plates limit the types of quantum fluctuations that can occur between them, creating an imbalance in the vacuum energy around them. This imbalance results in what can be interpreted as negative energy between the plates, producing the attractive force. While the effect is incredibly small, it provides experimental evidence that negative energy can exist under specific conditions, even if only in tiny amounts. The Casimir effect is an example of how quantum mechanics allows for the existence of phenomena that seem impossible in classical physics. In the context of warp drives, the hope is that negative energy could be generated on a much larger scale, potentially allowing us to manipulate space-time in ways that enable faster-than-light travel. However, the negative energy produced by the Casimir effect is far too small to be of any practical use for a warp drive. Scaling up this effect to the levels needed for space travel would require advances in our understanding of both quantum mechanics and energy production that we have yet to achieve. Quantum fluctuations themselves are another intriguing aspect of this phenomenon. These fluctuations are the result of the uncertainty principle in quantum mechanics, which states that even in a vacuum, particles can momentarily pop in and out of existence. This constant activity gives rise to a background energy that is always present, even in empty space. While quantum fluctuations are usually random and unpredictable, the Casimir effect shows that they can be manipulated under certain conditions. The ability to control these fluctuations and harness their energy is still far beyond our reach, but it opens the door to exciting possibilities in the future. The relationship between quantum fluctuations and negative energy is a central focus for researchers trying to understand how we might one day use these effects in practical applications. If we can learn to control these quantum phenomena, it could lead to breakthroughs in energy production, propulsion, and even faster-than-light travel. Another challenge is that while the Casimir effect provides evidence for negative energy, it doesn't offer a clear path toward producing the massive amounts needed for something like a warp drive. It's a glimpse into what might be possible, but the gap between current experimental results and the energy levels required for space travel remains vast. The Casimir effect also raises interesting questions about the nature of the vacuum itself. If even empty space is filled with quantum fluctuations and energy, then space is far more dynamic than we previously thought. This could mean that there are untapped resources or new physics waiting to be discovered in the fabric of space-time. Despite its limitations, the Casimir effect is one of the most significant real-world demonstrations of how quantum mechanics challenges our classical understanding of energy and space. It suggests that negative energy, while elusive, is not entirely beyond our reach. Quantum fluctuations and the Casimir effect remain at the cutting edge of physics research. They hint at new possibilities, but they also remind us of how little we still understand about the deeper workings of the universe. For now, they offer tantalizing clues, but the road to practical applications like warp drives is still a long one. Experimental evidence for negative energy is still incredibly limited, but there are a few key experiments that hint at its existence. The Casimir effect is perhaps the most well-known, providing direct evidence of a force that can be interpreted as negative energy in certain conditions. This small but measurable phenomenon shows that quantum fields can behave in unexpected ways. In the laboratory, the Casimir effect demonstrates how quantum fluctuations in a vacuum can generate forces between objects, implying the presence of negative energy. However, the effect is so weak that it only operates on a microscopic scale, making it far from the levels required for practical applications like a warp drive. Another area of interest is in the study of black holes and the Hawking radiation they emit. Theoretical predictions suggest that negative energy could be part of the process that allows black holes to slowly lose mass over time. While direct experimental observation of this negative energy is difficult, it provides a potential link between quantum mechanics and relativity. Scientists have also looked at the behavior of particles in high-energy accelerators, where extreme conditions sometimes reveal unusual quantum phenomena. Although these experiments haven't produced conclusive evidence of negative energy, they help to explore the limits of known physics, pushing the boundaries of what we understand. On a theoretical level, negative energy plays a role in certain solutions to Einstein's field equations in general relativity. These solutions, which include the Alcubierre warp drive and traversable wormholes, require negative energy to function. While these concepts are purely mathematical for now, they suggest that negative energy might be more than a theoretical curiosity. In quantum field theory, fluctuations of the vacuum can produce regions where negative energy temporarily appears. These fluctuations are short-lived, but they provide a glimpse into the possibility that negative energy could exist in controlled conditions. The challenge is finding a way to stabilize and harness this energy for practical use. Another area of exploration involves the idea of squeezing light, a quantum optics phenomenon that can create a situation where the energy in a particular region appears to be negative. While this is another microscopic effect, it adds to the growing body of experimental results that suggest negative energy isn't purely theoretical. Gravitational wave detectors have also been proposed as a way to search for exotic phenomena, including negative energy. The extreme sensitivity of these detectors could, in theory, detect tiny distortions in space-time caused by fluctuations of negative energy, although no direct evidence has been found yet. Some researchers have even speculated that cosmic phenomena, like the expansion of the universe driven by dark energy, might have some connection to negative energy. If this is true, it could mean that negative energy is already playing a role in the large-scale structure of the cosmos, though we have yet to observe it directly. Quantum entanglement, another area of quantum mechanics, may also hold clues. Some theories suggest that entangled particles could be influenced by negative energy across vast distances. While this remains speculative, it's another avenue where negative energy might one day be observed in experiments. Despite these intriguing hints, no experiment has yet provided large-scale, usable amounts of negative energy. The challenges of producing, detecting, and controlling it remain significant, and many of the experiments that suggest its existence are limited to extremely small or short-lived effects. For now, negative energy remains an elusive and mostly theoretical concept. While experimental evidence is building, we're still a long way from understanding how to harness it on the scale needed for technologies like warp drives, but the possibility remains an exciting frontier for future discoveries. Exotic matter, especially the kind needed for warp drives, is incredibly hard to find because it doesn't behave like normal matter. Normal matter has positive mass and energy, while exotic matter, in theory, would have negative mass or energy. This makes it behave in ways that are entirely different from anything we're familiar with. One reason exotic matter is so elusive is that it doesn't naturally exist in our everyday world. All the particles and forms of matter we've discovered so far have positive mass. Negative mass, if it exists, would behave in a way that defies our current understanding of gravity and motion. When we think about how exotic matter might behave, the differences become clear. For example, an object with negative mass would move in the opposite direction to any force applied to it. This is completely counterintuitive and suggests that, if exotic matter exists, it might be governed by a set of physical laws we don't fully understand. Current particle accelerators and experiments haven't yet detected any sign of negative mass particles, though they're looking. The kinds of conditions required to produce exotic matter might involve energy levels, or states of matter that we haven't yet been able to achieve. This makes the search for exotic matter a high-stakes challenge in experimental physics. There's also the possibility that exotic matter is inherently unstable. If it could be created, it might decay almost instantly, disappearing before we even have the chance to study it. This instability would make it incredibly difficult to detect, let alone harness, for something as complex as a warp drive. Even in quantum theory, where the concept of negative energy exists, exotic matter seems to only appear in highly specialized situations. Effects like the Casimir effect show hints of negative energy, but only at a microscopic scale. Scaling this up to something useful for space travel is a monumental task. Another difficulty is that the properties of exotic matter could make it dangerous or hard to contain. Negative energy or mass might interact with normal matter in unpredictable ways, potentially causing damage or annihilation. Without a way to safely store or control it, even if we found exotic matter, we wouldn't be able to use it. Theoretical physics also suggests that exotic matter might only exist under extreme conditions, such as near black holes or in the early moments of the universe. If this is the case, finding or creating exotic matter on Earth could be nearly impossible with current technology. While researchers are trying to uncover new particles through high-energy experiments, none have yet revealed anything that could be classified as exotic matter. The search is complicated by the fact that we don't know exactly what we're looking for. Without a concrete prediction of its properties, it's difficult to design experiments that might detect it. Even if we one day produce exotic matter in a laboratory, the amount needed for something like a warp drive would be far greater than what we can create with current methods. This gap between theory and practical application is one of the major reasons exotic matter remains out of reach. The universe might hold exotic matter in some distant corner, but the challenge is figuring out where to look. It could be that exotic matter is incredibly rare, or it might be hidden in forms we haven't yet imagined. Until we develop new technologies or theories, the hunt for exotic matter will continue to be a difficult pursuit. For now, exotic matter remains largely theoretical, with only hints of its existence in specialized experiments. Until we overcome the barriers to finding or creating it, warp drives and other technologies dependent on exotic matter will stay firmly in the realm of science fiction. The energy consumption required for a warp drive is one of the biggest obstacles to making faster-than-light travel a reality. Early estimates suggest that the amount of energy needed could be astronomical. Some calculations propose that it might require energy equivalent to the mass of entire planets or even stars just to generate a small warp bubble. These estimations are based on the idea that warping space-time requires negative energy, which is incredibly hard to produce in significant amounts. The vast quantities of energy would need to create and sustain the warp bubble as it moves through space, compressing and expanding space-time in a controlled manner. For example, one early study suggested that to power a warp bubble large enough for a spacecraft, you'd need more energy than the Sun produces in its entire lifetime. That level of energy consumption is beyond anything humanity can even conceive of producing with current technology. More recent research has tried to reduce these figures by altering the shape of the warp bubble in the theoretical model. By optimizing the geometry, some scientists believe the energy requirements could be brought down. But even with these adjustments, the energy needed remains far beyond our capabilities. Even the most advanced energy generation technologies we have today, such as nuclear fusion or antimatter, would fall dramatically short. To meet the theoretical energy demands for warp travel, we'd likely need an entirely new form of energy production, something on a scale we've never achieved before. Some researchers have looked to harness the energy of stars, or tap into the vacuum energy of space itself, known as zero-point energy. These sources, while abundant in theory, present their own challenges. We don't currently know how to extract or use such energy in the amounts that would be required for a warp drive. The challenge is not just in producing enough energy, but in storing and controlling it. The energy required for warp travel would need to be both immense and precisely directed to maintain the stability of the warp bubble over long distances. Managing such vast amounts of energy without catastrophic failure is a significant technological hurdle. Another factor in the high energy consumption is the fact that the warp bubble would have to be maintained for the entire duration of the journey. The longer the distance you want to travel, the more energy you'd need. This means that for interstellar travel, the energy demands grow exponentially. Additionally, the energy requirements for starting and stopping the warp bubble are unknown. It's not just a matter of powering the ship through space, but also controlling how the bubble forms and dissipates at the beginning and end of the journey. The energy involved in these transitions could be just as great as during the travel itself. Some estimates also suggest that traveling at faster than light speeds could have unintended side effects that might increase energy demands. For example, interactions with particles or radiation in space could create resistance, requiring even more energy to keep the bubble moving smoothly through the cosmos. Ultimately, the energy consumption for a warp drive is a fundamental barrier. Until we find ways to produce and manage the required energy, faster-than-light travel remains a theoretical possibility. Without breakthroughs in energy technology, even the most refined models of warp travel will stay beyond our reach. Despite the daunting figures, research continues. Scientists are still exploring how to reduce the energy requirements, but for now, the numbers remain far too large for any practical application of warp drive technology. To grasp the scale of the energy required for a warp drive, it helps to compare it to Earth's total energy output. Currently, the entire human civilization uses around 580 million terajoules of energy each year. This includes all electricity, fuel, and industrial power generated globally. Now imagine that powering a single warp drive could demand more energy than that, perhaps even thousands or millions of times more. The estimates for creating and sustaining a warp bubble are so high that the energy used by our planet over several centuries might not even come close. For perspective, the energy output of the world's largest power plants is measured in gigawatts, but that's still a fraction of what's needed. Generating enough energy for warp travel could require tapping into sources far beyond anything available to us, like harvesting energy directly from stars or other cosmic bodies. Another comparison is with the energy released by nuclear weapons. The most powerful nuclear bomb ever detonated released around 210 petajoules of energy. Even that massive explosion is still only a small fraction of what would be needed to power a warp drive for even a brief moment. To meet the energy requirements for warp travel using current technology would mean expanding our energy production exponentially. It's not just about producing more electricity. It's about accessing forms of energy that far exceed anything humanity has ever achieved. This kind of energy output isn't something we can easily generate with today's methods like fossil fuels or nuclear reactors. Even with renewables like solar or wind power, we're orders of magnitude away from what's needed to reach the theoretical energy demands of faster-than-light travel. Harnessing antimatter has often been suggested as a potential solution, since matter-antimatter reactions release far more energy than conventional fuels. However, the amount of antimatter we've been able to produce so far is minuscule, and storing it safely adds another challenge. Even if we somehow harnessed all the sunlight hitting the Earth, which amounts to around 174 petawatts, it still wouldn't be enough to power a warp drive continuously. This shows just how far beyond current human capacity the energy needs for warp technology are. The energy required might also exceed the theoretical limits of what our current technology can handle. The infrastructure needed to produce, store, and control such massive energy flows would be unlike anything we've ever built. It would require breakthroughs not just in energy production, but in physics and engineering as well. There's also the environmental impact to consider. If we were to somehow generate this level of energy using current technologies, it could have a profound effect on Earth's ecosystems, adding another layer of complexity to the challenge of making warp travel viable. Overall, when compared to Earth's total energy output, the energy needed for warp drives is staggering. Until we develop entirely new energy sources or methods of generation, the gap between our current capabilities and what's required for faster-than-light travel remains vast. The sheer scale of the energy problem is one of the key reasons why warp drives remain speculative. Without a major leap forward in our ability to harness and control energy, the dream of faster-than-light travel will remain out of reach for the foreseeable future. Negative mass is a hypothetical concept in physics that defies our everyday understanding of how objects behave. Unlike normal mass, which is attracted to other masses through gravity, negative mass would do the opposite. It would repel other masses, and when a force is applied to it, it would accelerate in the opposite direction. If negative mass exists, it could play a crucial role in the creation of a warp drive. Negative mass might generate the exotic energy needed to warp space-time, allowing faster-than-light travel. It's the kind of matter that could theoretically make it possible to expand space behind a spacecraft and compress it in front, forming the warp bubble. The strange behavior of negative mass would have significant implications. In theory, an object with negative mass could cancel out the effects of a positive mass object. This balance could create the kind of space-time distortions required for technologies like wormholes or warp drives to exist. One of the most bizarre consequences of negative mass is that if it were placed next to an object with positive mass, they would accelerate indefinitely. The positive mass would be pulled toward the negative mass, and the negative mass would be repelled, creating a feedback loop of motion. So far, no evidence for negative mass has been found in nature. It remains a purely theoretical concept, and many scientists question whether it could even exist in our universe. If it does exist, we've yet to discover where to find it or how to produce it. The implications of finding negative mass would go far beyond faster-than-light travel. It could revolutionize our understanding of gravity, inertia, and the fundamental forces of the universe. Negative mass could change the way we approach everything from space travel to energy production. Some theories suggest that negative mass could interact with space-time in ways we've never imagined. It might be able to distort space on a massive scale, enabling the creation of stable wormholes or other shortcuts through space. This could open up entirely new possibilities for interstellar travel. However, controlling negative mass would be a major challenge. Its repulsive nature would make it incredibly difficult to contain or manipulate. Any interaction with positive mass could lead to unpredictable and potentially dangerous effects, especially when dealing with the high energy levels required for warp technology. There's also the question of how negative mass would interact with other forms of energy. If it behaves differently under the laws of physics, it could require new methods of energy transfer or propulsion. We might need to develop completely new technologies just to work with it. Negative mass could also have implications for the structure of the universe itself. Some theorists have proposed that dark energy, which drives the expansion of the universe, might be linked to negative mass in some way. If that's true, understanding negative mass could be key to solving some of the biggest mysteries in cosmology. While the concept remains speculative, it continues to be a topic of serious interest among physicists. If negative mass can be proven to exist, it could fundamentally alter the way we think about space, time, and the limits of human travel. The challenge is figuring out if it's more than just a theoretical possibility. For now, negative mass remains one of the most intriguing ideas in theoretical physics, with far-reaching implications for the future of science and technology. Whether it can be harnessed for warp travel or other purposes remains to be seen, but the possibilities are exciting to consider. Finding a viable energy source for warp technology is one of the biggest challenges facing scientists. Conventional energy sources like fossil fuels or nuclear power are nowhere near capable of generating the immense energy required to manipulate space-time. For warp technology to be feasible, we'll need to explore entirely new forms of energy. One of the most promising candidates is antimatter. When matter and antimatter collide, they annihilate each other, releasing massive amounts of energy. This reaction is far more powerful than any chemical or nuclear process we currently use. If we could harness antimatter in large quantities, it might provide the energy necessary for a warp drive. The problem with antimatter is that it's incredibly difficult to produce and store. Currently, we can only generate tiny amounts of antimatter in particle accelerators, and even then, the energy required to produce it outweighs the energy we get from it. Storing antimatter is another challenge since it would destroy anything it comes into contact with. Another theoretical energy source is zero-point energy. This concept comes from quantum mechanics and suggests that even in a vacuum, space is never truly empty. Instead, it's filled with a fluctuating energy field. If we could tap into this zero-point energy, it might provide an almost limitless power supply for advanced technologies like warp drives. However, extracting zero-point energy is purely speculative at this point. While some scientists believe it could be possible, we have no idea how to access or control it. The potential is there, but the technology to use zero-point energy may be centuries away. Fusion energy is another potential source for powering warp technology. Fusion, the process that powers stars, releases enormous amounts of energy by fusing atomic nuclei together. If we can achieve controlled nuclear fusion on Earth, It could provide the kind of energy needed for interstellar travel. The challenge with fusion energy is achieving and sustaining the high temperatures and pressures needed for the reaction. While researchers are making progress, we're still decades away from developing practical, large-scale fusion reactors. Even then, the energy output may not be enough for warp technology. There's also the idea of harnessing energy directly from stars. Dyson spheres or other megastructures could theoretically capture a star's energy output, providing a nearly unlimited power source. While this concept is far beyond our current technological capabilities, it's one of the few ideas that could meet the enormous energy demands of warp travel. Dark energy, the mysterious force driving the expansion of the universe, has also been proposed as a potential energy source. If we could understand and harness dark energy, it might offer a way to power warp drives. However, like zero-point energy, dark energy is still poorly understood, and we're nowhere close to being able to use it. Some scientists have even speculated about using black holes as energy sources. In theory, a rotating black hole could provide immense amounts of energy through what's known as the Penrose process. While this idea is intriguing, the technical challenges of approaching and harvesting energy from a black hole are almost unimaginable. Another idea involves using quantum entanglement or other quantum phenomena to transfer energy instantaneously across vast distances. While this concept is still in the realm of theory, breakthroughs in quantum physics could open up new possibilities for energy transmission that we can't yet foresee. In the end, the energy source for warp technology will likely come from something we've yet to fully understand or discover. Current technologies, even those in development, fall short of what's needed. But as we push the boundaries of physics and energy science, new possibilities may emerge that could one day make warp travel a reality. Current technology falls dramatically short of what's required to make warp drives a reality. Our most advanced propulsion systems rely on chemical or nuclear energy, both of which are nowhere near powerful enough to warp space-time. The energy demands for a warp drive exceed anything we can produce with existing methods. One major limitation is our inability to generate or store the immense amounts of energy needed for faster-than-light travel. Even our most efficient energy sources, like nuclear fusion, are still in development and would struggle to meet the requirements for sustaining a warp bubble. Additionally, we lack the capability to manipulate space-time itself. The theoretical models behind warp drives depend on creating a stable warp bubble, but we don't yet have the technology to bend or warp space in the controlled way that would be necessary for faster-than-light travel. The concept of negative energy, which is crucial to many warp drive models, is still entirely theoretical. We don't know how to produce negative energy on a large scale, let alone how to control it in a way that could power a spacecraft. Without solving this problem, the idea of creating a warp bubble remains out of reach. Another limitation lies in the materials needed for such a technology. The stresses involved in warping space could be enormous, and we don't yet have materials strong enough to withstand those forces. Current spacecraft designs would be torn apart by the energy required to form a warp bubble. We also don't have a way to shield a spacecraft from the dangerous effects of traveling at faster-than-light speeds. The ship would need protection from cosmic radiation, high-energy particles, and other hazards that become far more intense when moving through warped space-time. Communication during faster-than-light travel is another unsolved issue. Current technologies rely on signals that travel at the speed of light, which means a ship in a warp bubble would be cut off from any communication with the outside world. We'd need entirely new methods of communication to overcome this limitation. Beyond communication, navigation at faster-than-light speeds presents its own challenges. We don't yet know how to precisely steer or control a warp bubble. Without a reliable way to direct such a spacecraft, the risks of traveling through warped space would be enormous. Even if we had the energy and materials to create a warp bubble, sustaining it over long distances poses another problem. The longer a ship remains in the bubble, the more energy it would require to maintain the warp. Our current energy storage technologies aren't capable of providing continuous power on this scale. Safety is also a major concern. The release of energy when creating or collapsing a warp bubble could be catastrophic. Without a clear understanding of how to control this process, any attempt to build a warp drive would carry significant risks for both the crew and the surrounding environment. On top of these technical limitations, there's the question of cost. Developing the infrastructure needed to support warp travel would require a massive investment in research, materials, and technology. The financial and resource demands are beyond anything humanity has attempted before. In the end, the limitations of current technology show just how far we still have to go. While the concept of warp drives is compelling, the technological hurdles are immense. We're still many breakthroughs away from even the first steps toward making faster-than-light travel possible. NASA's EagleWorks lab is one of the few places actively researching the possibility of faster-than-light travel. Led by Dr. Harold "Sonny" White, this small team has been exploring advanced propulsion concepts that could one day make warp drives a reality. Their work focuses on the theoretical and experimental side of space-time manipulation. One of the lab's most notable projects is their research into the Alcubierre warp drive model. EagleWorks has been trying to refine the equations behind the concept, looking for ways to reduce the enormous energy requirements that make it impractical with current technology. This involves exploring new methods to manipulate space-time on a smaller scale. A key part of their work involves experiments with a device called a White-Jude warp field interferometer. This device is designed to detect tiny changes in space-time that could indicate the presence of a warp field. While no definitive results have been achieved, these experiments represent some of the first steps toward understanding how to manipulate space itself. In their research, EagleWorks has also been investigating the Casimir effect, which involves negative energy. By studying the behavior of quantum fluctuations in a vacuum, they hope to uncover insights that could eventually lead to the production of negative energy, a critical component of warp drive theories. The lab is working within the constraints of current technology, but their goal is to push the boundaries of what's possible. They're attempting to identify theoretical shortcuts that could make faster-than-light travel achievable with significantly less energy than originally thought. EagleWorks' work is highly speculative, but it has drawn attention from both the scientific community and the public. The idea of warp travel is captivating, and their efforts have sparked renewed interest in advanced propulsion technologies. While they haven't created a warp drive yet, they're laying the groundwork for future breakthroughs. The lab is also exploring other futuristic propulsion concepts, including the EM drive. This controversial device claims to produce thrust without the need for traditional fuel, potentially offering a new way to achieve high-speed space travel. Though the EM drive's results are still debated, it's part of their broader mission to investigate unconventional propulsion methods. EagleWorks operates on a modest budget, and much of its work remains theoretical for now. Still, their experiments and calculations are helping to refine the models behind warp travel, bringing us closer to understanding the practical challenges involved. While some critics argue that the lab's work is too speculative, EagleWorks remains focused on exploring ideas that might seem far-fetched today, but could become essential in the future. After all, many of humanity's greatest technological achievements began as speculative concepts. One of the major hurdles the lab is addressing is the enormous energy requirement for a warp drive. By tweaking the equations and searching for new ways to reduce energy consumption, they aim to bring the theoretical demands closer to something feasible with future technologies. NASA's EagleWorks lab is still in the early stages of this research, but their work could pave the way for future generations to develop technologies that make faster-than-light travel a reality. They're working at the intersection of science fiction and science fact, trying to transform what was once pure imagination into the realm of possibility. Though the dream of warp travel is still far off, EagleWorks' efforts remind us that even the most ambitious goals start with small steps. Their research keeps the conversation about faster-than-light travel alive, inspiring scientists and enthusiasts to keep looking toward the stars. Harold "Sonny" White has been one of the most prominent figures in the push for faster-than-light travel research. His work at NASA's EagleWorks lab has been dedicated to studying advanced propulsion systems, and he's best known for revisiting the Alcubierre warp drive model. White's contributions have helped refine our understanding of what might be possible with warp technology. One of White's key insights was his proposal to modify the original warp drive equations. By altering the geometry of the warp bubble, he suggested that the energy requirements could be significantly reduced. His work showed that instead of needing the mass energy of a planet, the drive might only require the energy equivalent to a small space probe. This reduction in energy needs reignited interest in warp drive technology. White's modifications made the concept seem slightly more feasible, though it's still far from achievable with current technology. His work represents an important step in moving the theoretical conversation forward. White has also focused on the importance of experimental validation. Through his leadership at Eagleworks, he directed experiments that aimed to detect small distortions in space-time, which could point toward the early formation of a warp bubble. These experiments, though still inconclusive, marked the first real-world attempts to test warp drive concepts. In addition to his work on warp drives, White has explored other unconventional propulsion ideas. He was involved in researching the EM drive, a controversial propulsion system that, if proven effective, could change the way we think about space travel. Though the EM drive remains highly debated, White's willingness to explore the unknown has kept NASA at the forefront of speculative propulsion research. White's contributions go beyond equations and experiments. He's been a key figure in keeping the discussion around advanced propulsion systems alive, often speaking publicly about the possibilities of warp technology. His presentations and talks have inspired both scientists and the general public, helping to bring credibility to what might otherwise be dismissed as science fiction. A significant aspect of White's work has been his ability to collaborate across disciplines. He's worked with theoretical physicists, engineers, and quantum mechanics researchers to explore how different areas of science might contribute to making warp drives a reality. This interdisciplinary approach is crucial for tackling such a complex problem. White has also emphasized the importance of a long-term vision. While he acknowledges that warp drive technology is far beyond our current capabilities, he sees his work as laying the foundation for future generations of scientists. He often speaks of warp travel as a possibility for centuries from now, but his contributions are making sure we're taking the first steps in that direction. His work has not been without criticism. Some in the scientific community argue that focusing on warp drives is too speculative and distracts from more immediate goals in space exploration. White, however, maintains that pushing the boundaries of what's possible is essential for innovation, and that we need to explore all avenues, even those that seem far-fetched. White's contributions have also opened doors for private sector interest in advanced propulsion research. His work has sparked discussions in both aerospace companies and academic institutions about the future of faster-than-light travel, bringing in new funding and resources to an area that once seemed too speculative to invest in. Although warp drives remain in the theoretical realm, White's persistence and vision have ensured that the conversation around faster-than-light travel continues. He's helped build a foundation for future discoveries that could one day make interstellar travel a reality. Harold Sonny White's work is a testament to the importance of daring to dream big. By challenging conventional thinking and working at the edge of what's possible, he has made a lasting impact on the field of advanced propulsion and space exploration. His contributions will likely inspire future breakthroughs, even if the final destination of warp travel is still far away. Ongoing theoretical and experimental studies in faster-than-light travel continue to explore the feasibility of concepts like warp drives. While many of these studies remain speculative, they are slowly expanding our understanding of space-time manipulation and advanced propulsion technologies. Researchers are refining existing models while searching for new breakthroughs. Physicists are focusing on better understanding the energy requirements of warp travel. Some are working on alternative mathematical models that could reduce the energy needed to create a warp bubble. These refinements are crucial if we ever hope to move from theoretical concepts to practical applications. In parallel, quantum mechanics remains a promising area of research. Some physicists are investigating how quantum fields and vacuum fluctuations might play a role in generating the exotic matter needed for warp technology. Although this research is still in its infancy, it could provide key insights in the future. Other experimental studies are looking at small-scale space-time distortions. Scientists are using interferometers and other high-precision tools to detect any signs that space-time can be manipulated in a controlled manner. These experiments are early steps, but they are helping to lay the groundwork for future technologies. While the focus remains on warp drives, some research is also investigating related concepts like wormholes. Wormholes, if stable, could act as shortcuts through space, offering another potential method of faster-than-light travel. These studies are exploring whether negative energy could keep a wormhole open long enough for practical use. Collaboration between international space agencies is becoming more common in this field. NASA, ESA, and other organizations are sharing data and ideas to advance the theoretical and experimental study of advanced propulsion. This global approach is key, as the challenges of faster-than-light travel are too vast for any one group to tackle alone. No, private companies are also getting involved in the research. Some aerospace firms are investing in advanced propulsion technologies, exploring how they could eventually lead to practical applications in space exploration. Though still focused on near-term technologies, these companies are keeping an eye on the long-term possibilities of faster-than-light travel. Theoretical studies are also pushing the boundaries of what we know about the laws of physics. Some researchers are questioning whether the speed of light is an absolute limit, exploring alternative frameworks in physics that might allow for faster-than-light phenomena. While controversial, these studies are essential for expanding our understanding of the universe. Another area of interest is energy harvesting from cosmic phenomena. Some scientists are studying whether energy could be drawn from sources like black holes, or even the expansion of the universe itself. These ideas are highly speculative, but if successful, they could provide the enormous power needed for warp drives. Computational simulations are playing a key role in ongoing research. Scientists are using powerful supercomputers to model space-time distortions, testing how different warp bubble configurations might behave. These simulations allow researchers to explore ideas that would be impossible to test in physical experiments for now. There's also interest in how advanced propulsion might impact human biology. Some studies are exploring the potential effects of traveling through distorted space-time on the human body, including how to shield passengers from radiation or other dangers. This is a critical step if warp travel is to be safe for humans. Although these studies are in their early stages, they represent a growing commitment to exploring faster-than-light travel. Each experiment and theoretical advance brings us closer to understanding whether technologies like warp drives can ever become a reality. For now, the journey continues. The private sector is beginning to show interest in the possibilities of faster-than-light travel and advanced propulsion systems. While most of the focus remains on more immediate technologies, some companies are investing in long-term research. These efforts are still small, but they signal a growing belief that faster-than-light travel could one day be possible. Several aerospace firms are exploring advanced propulsion as part of their long-term vision for space exploration. Companies like SpaceX and Blue Origin have ambitious plans to push the boundaries of space travel, and while their current projects focus on near-Earth missions, there is increasing interest in what comes next. Private sector funding could be key to accelerating research in this field. Government agencies like NASA often face budget constraints, limiting the resources they can dedicate to speculative research. Private companies, on the other hand, have more flexibility to invest in cutting-edge technologies, even those that are far from practical application. These companies are not just funding basic research, they're also interested in how advanced propulsion might impact commercial space travel. If faster-than-light travel ever becomes viable, it could revolutionize industries like satellite deployment, asteroid mining, and interplanetary tourism. The potential economic benefits are enormous. Venture capitalists are also starting to pay attention to the possibilities of warp drives and other advanced propulsion concepts. While these investors understand the risks, they see the long-term payoff as potentially transformative. In the world of technology and innovation, big breakthroughs often come from bold investments. Some private research institutions are partnering with academic and government organizations to share knowledge and resources. This collaboration is essential, as faster-than-light travel requires breakthroughs in both physics and engineering. By pooling resources, the private and public sectors can advance this research more quickly. The involvement of the private sector is also driving innovation in energy technologies. Companies are looking into alternative energy sources that could one day power advanced propulsion systems. This includes everything from antimatter research to more speculative ideas like zero-point energy. A few startups are emerging with a specific focus on futuristic propulsion systems. These companies, while small, are working on the fringes of what's possible, experimenting with concepts that larger, more risk-averse corporations might avoid. They are hoping to be the first to crack the code of faster-than-light travel. Some in the private sector are also exploring how these technologies might change defense and military applications. Faster-than-light travel would fundamentally alter the landscape of national security, enabling rapid response and transport across vast distances. Governments are beginning to take notice of the potential strategic advantages. The private sector's interest is not just financial. Many of the leaders in these companies are visionaries who see faster-than-light travel as the next great leap for humanity. They're driven by the desire to push human civilization beyond our solar system and explore the stars. The involvement of private companies has also brought a sense of competition to the field. With multiple organizations working on advanced propulsion, the race to develop these technologies is intensifying. This competition could drive rapid advancements, much like the early days of space exploration during the Cold War. While still in its early stages, private sector interest and funding in faster-than-light travel are steadily growing. These investments are helping to sustain research efforts that might otherwise struggle for resources, and they are bringing new energy to the quest for interstellar exploration. Currently, what's feasible in the lab for faster-than-light travel is still very limited. Most of the experiments being conducted today are focused on small-scale demonstrations of space-time manipulation or testing theories that might one day lead to advanced propulsion systems. These are early steps, but they're essential for building a foundation. One of the few tangible experiments involves trying to detect tiny distortions in space-time. Using devices like interferometers, researchers are attempting to observe whether it's possible to create or influence these distortions in a controlled environment. While no definitive results have been achieved, this kind of work is critical for understanding the potential of space-time manipulation. Quantum mechanics is also playing a significant role in laboratory experiments. Researchers are exploring phenomena like the Casimir effect, which shows how quantum fluctuations in a vacuum can generate small forces. Though the forces are weak, they offer clues about how space-time might be manipulated on a larger scale in the future. Testing warp drive concepts directly is far beyond our current capabilities, but simulations and models are being run to refine the theoretical framework. These simulations help scientists understand the conditions under which a warp bubble might form and what kind of energy would be required to sustain it. There's also ongoing research into exotic materials that might one day be used in advanced propulsion systems. While the exotic matter needed for a warp drive is still purely theoretical, the exploration of new materials and quantum states could eventually provide insights into what's possible. In the area of energy production, some experiments are focused on generating and controlling high-energy systems. While we're not close to creating the immense energy levels needed for warp travel, labs are working on pushing the boundaries of energy storage and transfer, which could have applications for future propulsion technologies. Researchers are also testing new types of propulsion systems that, while not faster than light, could significantly increase the speed and efficiency of space travel. These experiments, including ion drives and nuclear fusion propulsion, represent the most feasible near-term advancements that could one day bridge the gap toward more advanced systems. Laboratory studies on negative energy are still in their infancy. Scientists are attempting to understand how to create and stabilize negative energy fields, which are essential for warp drive theories. While the results so far are inconclusive, this area of research is receiving more attention as the theoretical need for negative energy becomes clearer. The study of antimatter continues to be a focus in some labs, as it's one of the most efficient known sources of energy. Though antimatter production remains incredibly difficult and costly, researchers are making small strides in understanding how to produce and potentially store it in larger quantities. Another area of exploration is the control of gravitational forces on a small scale. While we can't yet manipulate gravity in any meaningful way, experiments with gravity waves and quantum field interactions may someday offer new methods for propulsion based on gravitational manipulation. In terms of practical application, most of what's happening in labs today is still theoretical and experimental. No one has yet built anything resembling a working warp drive, but the research is laying the groundwork for what might be possible in the future. Incremental progress is being made, but it's a long road ahead. Overall, the feasibility of faster-than-light travel remains distant, but the work being done in laboratories today is providing crucial insights. Each experiment, each model, and each simulation moves us closer to understanding whether warp technology could one day be achievable. For now, the breakthroughs are small, but they are important steps in the right direction. If warp drives become a reality, They could revolutionize space exploration in ways we can hardly imagine today. Traveling faster than light would allow us to reach distant planets, stars, and galaxies in a fraction of the time it currently takes. This would completely change the way we think about space missions. Instead of planning for decades-long journeys to the nearest star systems, we could explore them within a human lifetime. Warp technology would open the door to interstellar exploration, making it possible to visit planets orbiting other stars, and even establish colonies far beyond our solar system. The ability to move through space at faster than light speeds would also transform the logistics of space travel. Supply missions, rescue operations, and communication with distant outposts would no longer be constrained by the speed of light, allowing for faster response times and better coordination across vast distances. With the ability to travel between star systems quickly, the search for extraterrestrial life could take on an entirely new dimension. Instead of relying on telescopes and probes, we could send manned missions to explore potentially habitable planets directly, increasing the chances of discovering life beyond Earth. Warp drives could also lead to the development of space tourism on an unprecedented scale. Once the technology is safe and reliable, it might be possible for civilians to travel to distant planets or even other star systems, turning what was once science fiction into a new frontier for adventure and exploration. Scientific research in space would benefit enormously from faster-than-light travel. We could place scientific instruments on distant planets or in unexplored regions of space, collecting data from areas that are currently beyond our reach. This could lead to breakthroughs in our understanding of the universe's origins and structure. Mining asteroids and other celestial bodies for resources would become much more practical with warp technology. The ability to travel quickly between Earth and resource-rich areas in space would open up new opportunities for harvesting materials that are scarce or depleted on our planet. The military implications of faster-than-light travel are also significant. Nations could deploy defense systems or spacecraft at previously unimaginable speeds, fundamentally altering the strategic balance in space. This would lead to new discussions about the ethics and regulations of space travel. Warp drives could help humanity address existential threats. If we ever face a planet-wide catastrophe or the long-term effects of climate change become irreversible, warp technology could allow us to evacuate Earth and establish new homes elsewhere in the galaxy. Exploring space on such a vast scale would also encourage international cooperation. The development and use of warp drives could require collaboration between nations, leading to shared exploration missions and global efforts to advance our understanding of the cosmos. If we achieve faster-than-light travel, the sheer scale of the universe will no longer be an insurmountable obstacle. Entire regions of the galaxy that are currently out of reach could become accessible, offering new opportunities for discovery, exploration, and perhaps even interaction with other intelligent species. Ultimately, warp technology would redefine what it means to explore space. The limitations that have held us back for so long, distance, time, and energy, would be diminished, opening up a universe of possibilities for human exploration and expansion. The impact on science, culture, and the future of humanity would be profound. Warp drive technology would unlock the potential for true interstellar travel, something that has only been a distant dream. Instead of taking thousands or even millions of years to reach other stars, we could cross vast distances in a matter of days, weeks, or months. The nearest star systems would become reachable destinations. Proxima Centauri, the closest star to our solar system, is currently over 4 light-years away. With current technology, it would take over 70,000 years to get there. But with a functioning warp drive, this journey could be reduced to just a few years or even less, making interstellar exploration feasible. The discovery of potentially habitable exoplanets, like those in the TRAPPIST-1 system, has heightened interest in interstellar travel. With faster-than-light capabilities, we could send missions to these planets to assess their environments and explore whether life exists beyond Earth. This could be the start of a new era in the search for alien life. Interstellar travel wouldn't just be limited to exploration. If we could reach other star systems, colonization could become a real possibility. Humans could establish permanent settlements on planets orbiting distant stars, ensuring the survival of our species even if Earth faces existential threats. The ability to travel between stars would also allow for resource gathering on an unprecedented scale. We could mine asteroids, moons, and planets in other systems for rare elements, water, and other valuable materials. These resources could support not only life on Earth, but also new colonies in distant star systems. Exploring multiple star systems would give us a much broader understanding of the galaxy. We could investigate how different solar systems form, compare planetary environments, and gather new data on the forces that shape the universe. Each new system we visit would reveal more about the cosmos. Interstellar travel could also lead to the discovery of new natural phenomena. We might encounter different types of stars, planets with unusual properties, or even phenomena that challenge our understanding of physics. Every star system could hold surprises that change our perspective on the universe. Reaching other stars would allow us to expand our technological horizons. The challenges of interstellar travel would push us to develop new systems for communication, life support, and energy generation. These advances could have applications far beyond space travel, transforming life on Earth as well. There's also the possibility that faster-than-light travel could allow us to communicate with distant civilizations. If there are intelligent species in other parts of the galaxy, reaching them has been impossible due to the vast distances involved. Warp drives could bridge this gap, leading to the potential for first contact. Interstellar travel might also reveal new opportunities for scientific collaboration. As we explore further into space, the need for international partnerships would grow. The vast scale of the galaxy would encourage cooperation among nations and organizations, promoting unity through shared exploration goals. Traveling between stars would change how we view time and distance. Entire new worlds could become part of humanity's reach, and what once seemed like impossible distances would shrink. This could shift our entire cultural outlook, reshaping our sense of place in the universe. Ultimately, the possibilities of interstellar travel are limitless. Each step toward unlocking faster-than-light travel brings us closer to a future where humans explore not just our solar system, but the entire galaxy. The ability to travel between stars could redefine our understanding of the cosmos and our place within it. Colonizing other star systems would be one of the most profound outcomes of faster-than-light travel. With the ability to move between stars, humanity could establish settlements on distant planets, ensuring the survival of our species across multiple worlds. This would mark the beginning of humanity's expansion beyond our solar system. Finding suitable planets would be the first challenge. With faster-than-light travel, we could send missions to assess exoplanets for habitability. Some of these worlds may already have the right conditions for life, while others might require terraforming to make them livable for humans. Once a suitable planet is found, building the infrastructure for a colony would be a monumental task. Everything from life support systems to energy sources would need to be set up, but with warp drives, we could transport the necessary equipment and personnel more efficiently than ever before. It would allow for regular supply missions and faster development. These colonies could serve as launching points for further exploration. Once we have a foothold in another star system, it would become easier to expand even further into the galaxy. Each colony could become a hub for missions that reach deeper into the cosmos, pushing humanity's boundaries ever outward. Colonizing other star systems would offer a way to protect humanity from existential threats. A single disaster on Earth, whether natural or man-made, could wipe out civilization. But with colonies spread across multiple star systems, the survival of our species would no longer be tied to the fate of one planet. Interstellar colonies could also become centers of innovation. With new environments and challenges, scientists and engineers would be forced to develop new technologies tailored to different planetary conditions. These advancements could benefit both the colonies and life on Earth, driving progress in unexpected ways. Cultural diversity could flourish in these distant settlements. Colonists on other worlds might develop unique traditions, customs, and ways of life, shaped by the planets they inhabit. Over time, these differences could lead to a rich tapestry of human culture spread across the galaxy, united by a shared history, but distinct in its expression. Economic opportunities in these colonies could be vast. The resources of entire star systems would become available, providing materials that are rare or unavailable on Earth. Mining asteroids, moons, and planets for precious metals, water, and other resources could fuel both the economy of the colonies and Earth itself. The establishment of colonies would also encourage international cooperation. Building and sustaining a colony on another planet would require the resources and expertise of many nations working together. This could foster a new era of global unity, as the challenges of colonizing space would demand collaboration on an unprecedented scale. While the colonies would be independent in many ways, communication with Earth would remain essential. Faster-than-light travel could ensure that these distant worlds stay connected, allowing for the exchange of information, technology, and culture. A network of colonized planets could work together to ensure mutual survival and growth. Living in other star systems would change humanity's relationship with time and distance. What once seemed like insurmountable gaps between worlds would become manageable, leading to the possibility of trade, travel, and even tourism between planets orbiting different stars. The concept of home might expand to include not just Earth, but an entire galaxy. Ultimately, colonizing other star systems would represent the next great step in human evolution. It would allow us to transcend the limitations of our home planet, spreading out into the stars and ensuring that humanity continues to thrive no matter. Faster-than-light travel would have profound implications for military and defense strategies. The ability to move troops, ships, and supplies across vast distances almost instantaneously could redefine the balance of power in space. Nations and organizations that develop warp technology first would have a significant advantage. Warp drives could allow for the rapid deployment of forces to distant locations, responding to threats or conflicts in other star systems with unprecedented speed. This capability would make it possible to defend colonies or outposts spread across the galaxy without the long delays currently associated with space travel. Stealth would take on a new meaning in warfare. A fleet of ships equipped with warp drives could appear without warning in any star system, bypassing traditional detection methods. This ability to strike suddenly and retreat just as quickly would create a whole new dynamic in space-based military engagements. Defensive strategies would need to evolve in response. Planetary defense systems would have to be designed to detect and counter faster-than-light incursions. Space-based sensors, early warning systems, and automated defense platforms would become crucial in protecting assets spread across different star systems. Warp technology could also enable the rapid construction of military bases in strategic locations. With the ability to transport materials and personnel faster than light, nations could quickly establish outposts in resource-rich or tactically valuable areas, solidifying their presence and control over key regions of space. Supply lines, a critical aspect of military logistics, would become much more efficient. Instead of slow, vulnerable convoys stretching across vast distances, supplies could be delivered directly to the front lines or distant outposts in record time. This would allow for sustained military operations far from Earth. The potential for warp-enabled weapons platforms is another significant consideration. Faster-than-light travel could enable the deployment of weaponry to remote locations instantly, allowing for strikes on distant targets with little chance of interception. This would raise important questions about the ethics and regulations of space-based warfare. The race to develop warp technology would likely spark a new kind of arms race, as nations vie for supremacy in space. The country or organization that first develops reliable faster-than-light travel would hold a tremendous advantage, potentially shifting the global balance of power. This could lead to increased competition and tension on a geopolitical scale. International agreements and treaties would be essential to prevent the militarization of faster-than-light technology. The ability to project military power across star systems could escalate conflicts if not carefully regulated. Global cooperation would be necessary to establish rules governing the use of warp drives in defense and warfare. However, the same technology could also be used for peacekeeping purposes. Faster-than-light travel could allow for rapid intervention in humanitarian crises or natural disasters, enabling peacekeeping forces to stabilize regions and provide aid in situations that would otherwise be inaccessible or too remote to reach quickly. Defending against faster-than-light threats would likely drive technological innovation. New forms of detection, tracking, and counter-warp technologies would be developed to safeguard against unexpected attacks. This could lead to a new generation of defense systems tailored specifically for interstellar warfare. Ultimately, the military and defense applications of faster-than-light travel would reshape how nations think about security in space. The ability to move forces and resources at superluminal speeds would require entirely new strategies, technologies, and international agreements to ensure that warp technology is used responsibly and safely in the defense of human interests. The development of warp drive technology would mark a turning point in humanity's future. It would push us beyond the boundaries of our solar system, transforming us into an interstellar civilization. The ability to travel between the stars could redefine what it means to be human. One of the most profound impacts would be on our sense of identity. As we begin to inhabit multiple star systems, we might see ourselves less as citizens of a single planet and more as members of a galactic community. Our relationship with Earth could shift as we explore new worlds and establish homes among the stars. The challenges we face on Earth, such as resource scarcity and overpopulation, could be alleviated by expanding into space. With entire planets and star systems to explore and colonize, we would have access to new resources and environments, giving humanity room to grow and evolve. Social structures could evolve in response to living on multiple planets. Governments, economies, and cultures might change dramatically as humans spread out across the galaxy. Each colony could develop its own way of life, shaped by the conditions of its new home and the experiences of its inhabitants. Warp drive technology could also lead to breakthroughs in other areas of science and technology. The quest for faster-than-light travel would likely push advancements in energy, materials science, and communication, with benefits that extend far beyond space travel. These innovations could have a profound effect on life on Earth. Culturally, the ability to explore new worlds could inspire a new era of art, literature, and philosophy. Just as the space race of the 20th century fueled dreams of space exploration, the reality of traveling between stars could spark a wave of creative expression, with people imagining what it means to live among the stars. There's also the possibility of encountering intelligent life. If warp drives allow us to explore distant star systems, we might discover civilizations beyond our own. First contact with another intelligent species would have an immeasurable impact on our worldview, reshaping our understanding of life in the universe. At the same time, warp technology would challenge us to think about the ethical implications of exploring and colonizing other worlds. Questions about the rights of potential alien life, the impact on untouched ecosystems, and the responsible use of technology would become pressing issues for future generations. Economically, the ability to access new star systems could open up vast new markets and opportunities. Mining asteroids, harvesting energy from distant stars, and developing new space industries could lead to unprecedented economic growth, reshaping the global economy in ways we can only begin to imagine. Our relationship with time would change as well. The distances between star systems, once thought insurmountable, would shrink with warp technology. Journeys that once took years or centuries could be completed in a matter of days or weeks, altering how we think about travel and communication on a galactic scale. Exploring new worlds could also foster a renewed sense of curiosity and wonder. As we push deeper into the unknown, the mysteries of the universe would drive humanity to continue seeking knowledge and understanding. The desire to explore, to learn, and to discover would become an even more central part of our future. In the long term, the impact of warp drives could ensure humanity's survival. By spreading across the galaxy, we would reduce the risks associated with being tied to a single planet. Warp technology could be the key to ensuring that humanity thrives for millennia to come, far beyond the boundaries of our current existence. There are significant technological hurdles standing in the way of creating a functional warp drive. The most pressing challenge is the immense energy requirement. Current models suggest we would need more energy than anything we can currently produce, possibly even more than the energy contained within an entire planet. Another major issue is the lack of a practical way to manipulate space-time. Warp drive theories rely on the ability to stretch and compress space, something we have no technology for. Our understanding of how to control space-time on a macro scale is still theoretical, and translating that into real-world technology is a daunting task. We also need to develop materials that can withstand the extreme conditions involved in faster-than-light travel. The forces generated by warping space could be enormous, and current spacecraft materials wouldn't be able to survive the journey. New materials with unprecedented strength and resilience would be required. The challenge of creating and harnessing exotic matter remains one of the biggest unknowns. For a warp drive to work, it would likely need negative energy or negative mass, neither of which has been observed or produced in a lab. Theoretical physics suggests it's possible, but turning that into reality is another matter entirely. Communication during warp travel would also present significant challenges. Our current systems rely on signals that travel at the speed of light, but in a warp bubble, those signals could be blocked or distorted. We'd need to invent new methods for sending and receiving information across vast distances at superluminal speeds. There's also the issue of navigation. Piloting a spacecraft at faster-than-light speeds requires precise control, but with space and time warping around the ship, it's unclear how to steer or adjust course. Developing a reliable system to guide a ship safely through warped space would be critical. Another technological hurdle is ensuring the stability of the warp bubble itself. Even if we could create one, keeping it stable during a journey would be a monumental task. The bubble could collapse, releasing immense energy and destroying the ship in the process, so maintaining control over this structure would be essential. Safety concerns are also significant. The energy released when a warp bubble forms or collapses could have dangerous consequences for the spacecraft and anything nearby. Developing safe procedures for initiating and ending faster-than-light travel would be necessary to prevent catastrophic accidents. The effects of time dilation during faster-than-light travel are another issue. While the ship may not experience it, the rest of the universe might. This could create complications for communication, aging, and synchronization with Earth-based systems, leading to logistical and operational difficulties. We'd also need to figure out how to protect the spacecraft and crew from high-energy particles and radiation. Traveling at faster-than-light speeds might expose the ship to cosmic forces that we haven't yet fully understood. Shielding the crew from these dangers would be a top priority for any successful mission. Developing the infrastructure to support faster-than-light travel would be another challenge. New spaceports, maintenance systems, and energy generation facilities would need to be built. It would require an enormous global effort to create the support structures necessary for regular warp travel. Finally, cost is a major technological hurdle. Even if we solve the scientific problems, the financial cost of building, powering, and maintaining a warp drive system could be astronomical. Finding ways to make the technology scalable and affordable would be essential for it to become a reality. Funding and international cooperation will be crucial to overcoming the challenges of developing warp drive technology. The sheer scale of the research and resources required means that no single country or organization can tackle it alone. Global collaboration will be essential for pooling expertise, funding, and infrastructure. Governments around the world would need to allocate significant financial resources to fund this research. Warp drive technology would require investment in both basic scientific research and applied engineering, and the costs would be enormous. This would likely involve international agreements to share the financial burden and the technological rewards. Private sector involvement could play a major role in funding, especially with companies in the aerospace and technology industries showing interest in advanced propulsion systems. These companies might contribute their own funds to the research in exchange for potential future profits or intellectual property rights related to the technology. International organizations such as the United Nations or a newly formed space alliance could help coordinate efforts. By setting up frameworks for collaboration, these groups could ensure that warp drive research benefits humanity as a whole, rather than becoming the exclusive domain of a few powerful nations or corporations. Global partnerships in science have already demonstrated how effective collaboration can be, as seen with the International Space Station and the Large Hadron Collider. Warp drive development would require similar levels of cooperation, with nations sharing knowledge and resources to achieve a common goal. There would also need to be agreements about the ethical use of faster-than-light technology. International laws and treaties would have to govern how warp drives are developed and deployed, preventing misuse or the monopolization of this potentially transformative technology by any single nation or entity. Funding research into alternative energy sources will be key, as current energy systems are not capable of supporting warp technology. International efforts to advance fusion energy, antimatter production, and other high-energy solutions could be directly tied to the development of faster-than-light travel. Academic institutions from around the world would play a central role in conducting the theoretical research and experiments needed to bring warp technology closer to reality. International collaboration between universities could accelerate discoveries, as scientists share data and work together to solve the biggest hurdles. Public support would be crucial for maintaining funding over the long term. Governments would need to ensure that citizens understand the potential benefits of warp drive research. Educational campaigns and public outreach programs could help generate enthusiasm and ensure continued investment in this long-term project. Global cooperation would also help manage the risks associated with warp technology. By working together, nations can ensure that safety protocols, ethical guidelines, and technical standards are established from the outset, minimizing the chance of accidents or unintended consequences. International space agencies such as NASA, ESA, and Roscosmos already collaborate on space exploration. These partnerships could be expanded to include joint warp drive research programs, allowing the best minds from each agency to contribute to the development of this groundbreaking technology. The race to develop faster-than-light travel could spark a new era of peaceful competition and collaboration. Just as the space race of the 20th century led to incredible scientific advancements, a new global effort to develop warp technology could unite nations in pursuit of a common, inspiring goal. One of the biggest challenges in developing warp drive technology is the theoretical conflict with established physics. Faster-than-light travel directly contradicts Einstein's theory of relativity, which states that nothing can exceed the speed of light. This fundamental limit has been a cornerstone of modern physics for over a century. Relativity predicts that as an object approaches the speed of light, its mass increases exponentially, requiring infinite energy to accelerate beyond this point. This creates a seemingly unbreakable barrier that any warp drive would need to overcome or circumvent without violating these laws. Warp drive theories, such as the Alcubierre drive, try to get around this by bending space-time itself, rather than moving the object through space. However, the idea of manipulating space-time on such a scale brings its own set of challenges, many of which remain unresolved within the framework of general relativity. The introduction of negative energy or exotic matter is another conflict. While it's a theoretical requirement for many faster-than-light concepts, there is no experimental evidence that such energy or matter exists in the quantities needed. Its existence would challenge some of our most fundamental assumptions about the nature of the universe. Quantum mechanics, which governs the behavior of particles at the smallest scales, also doesn't easily align with faster-than-light travel. The quantum world operates on principles that seem incompatible with bending space-time on a macroscopic scale, raising questions about how these two realms of physics interact when it comes to warp drives. Time travel is another theoretical issue that arises with faster-than-light travel. According to relativity, moving faster than light could allow for backward time travel, creating paradoxes like the grandfather paradox. Resolving these paradoxes would require a new understanding of time itself, which current physics cannot fully explain. Another conflict arises with causality, the principle that cause must precede effect. Faster-than-light travel could disrupt the sequence of cause and effect, potentially leading to scenarios where events happen out of order, further complicating the already delicate balance of theoretical physics. Even the idea of a stable warp bubble introduces problems. While the concept is mathematically intriguing, maintaining the stability of such a bubble over long distances or during rapid movement could violate known laws of thermodynamics, which govern energy use and efficiency. The energy required for warp travel, as theorized, also presents a conflict. The immense amounts of energy needed would challenge the limits of energy conservation, a bedrock principle of physics. How to produce and manage that energy without breaking fundamental laws remains an open question. Current physics doesn't provide a clear way to transition from sublight speeds to faster-than-light speeds without encountering infinite energy requirements. This gap between existing theories and what would be needed for warp technology creates a major theoretical roadblock. Some physicists suggest that a new theory of everything, one that unifies quantum mechanics with general relativity, might hold the key to resolving these conflicts. Until such a theory is discovered, faster-than-light travel will remain at odds with our current understanding of the universe. In the meantime, these theoretical conflicts are what make warp drive research so challenging yet exciting. They push the boundaries of what we know and force us to rethink some of our most fundamental scientific principles. The answers, if they come, will likely reshape physics as we know it. Faster-than-light travel, while promising, raises numerous ethical issues that humanity would need to address before widespread adoption. One of the most immediate concerns is the potential exploitation of other worlds. As we explore distant planets, we would need to consider the impact on any ecosystems or life forms that might exist there. The possibility of discovering intelligent extraterrestrial life complicates these ethical questions further. How we approach and interact with other civilizations could have profound moral implications. The decisions we make in these encounters could shape the future of interstellar relations, either fostering cooperation or leading to conflict. Another ethical issue revolves around resource extraction. If warp technology allows us to access planets rich in natural resources, we could be tempted to exploit them without consideration for the environmental consequences. Just as we've struggled with resource management on Earth, we would need to develop sustainable practices for space as well. There's also the risk of militarizing faster-than-light travel. Warp technology could be used to deploy weapons or wage war on a galactic scale, raising concerns about the balance of power and the potential for devastating conflicts. Developing international treaties and agreements would be essential to prevent misuse. Privacy concerns would also arise with faster-than-light travel. If we can cross vast distances instantly, surveillance and monitoring could become much more invasive, leading to new challenges in protecting individual freedoms and rights across the galaxy. The technology gap between nations or corporations could widen with the advent of warp travel. If only a few entities control the technology, they could monopolize space exploration, creating an imbalance of power and leaving smaller nations or organizations behind in the pursuit of interstellar opportunities. Ethical concerns would extend to the human impact of faster-than-light travel. If colonizing other planets becomes a reality, how do we ensure that new societies are inclusive, fair, and respectful of the environments they inhabit? The potential for exploitation or inequality in these colonies would need to be carefully managed. The long-term effects on human culture and identity could also raise ethical questions. As humans spread across different planets, cultural differences could become more pronounced. Ensuring that humanity remains united in purpose and cooperation, rather than fragmented by distance and differing priorities, would be a significant challenge. Intergenerational equity is another issue. The decisions we make about faster-than-light travel today could have lasting effects on future generations. We would need to balance the benefits of exploration and colonization, with the responsibility of ensuring a safe and sustainable galaxy for those who come after us. Ethical considerations would also need to include the risks of experimentation. As scientists work to develop warp technology, the potential for accidents or unintended consequences remains high. Ensuring that this research is conducted responsibly and with proper safeguards is critical to avoiding disastrous outcomes. Lastly, the broader philosophical question of why we seek faster-than-light travel must be addressed. Are we exploring the stars for the betterment of humanity, or are we driven by greed, power, or escape? Understanding our motivations will help us navigate the ethical complexities of this technological leap. In the end, addressing these ethical issues will require global cooperation, clear regulations, and a shared commitment to using faster-than-light travel for the good of all. Without careful consideration, the risks could outweigh the benefits, and the dream of exploring the stars could become a new frontier for moral dilemmas. The timeframes for realizing faster-than-light travel are difficult to predict, as the technology is still in the realm of theoretical physics. Some scientists believe that even the first steps toward developing a functional warp drive could be centuries away, while others remain cautiously optimistic about breakthroughs in the coming decades. One of the biggest factors influencing the timeline is the pace of advancements in energy production. The amount of energy required for warp travel far exceeds what we can generate today. It may take several generations before we develop energy systems capable of meeting the demands of such a technology. Theoretical work on warp drives is also progressing slowly. While there have been significant insights in the last few decades, much of the underlying physics remains speculative. More research is needed to determine whether the principles behind faster-than-light travel are even possible, let alone how to implement them. Another factor is funding. Major scientific breakthroughs often depend on sustained financial investment, and with the high cost of space research, warp drive development might not receive the funding it needs until other pressing challenges like energy and environmental concerns are addressed. Technological advances in other fields could accelerate the timeline. Discoveries in quantum mechanics, material sciences, or artificial intelligence could lead to unexpected breakthroughs that might bring warp technology closer to reality sooner than we expect. It's hard to predict how these fields will intersect with space travel. Public and political interest in space exploration will also play a role. If faster-than-light travel becomes a global priority, more resources and talent could be funneled into the research. Without strong public backing, however, the development of such ambitious technology might proceed more slowly. Human space exploration might act as a stepping stone. Developing long-term colonies on the Moon or Mars could provide valuable insights into propulsion, energy management, and life support systems, all of which are necessary components for faster-than-light travel. The lessons learned from these missions could influence the timeline. It's also possible that warp drive technology could arrive sooner than expected if a major breakthrough occurs. Throughout history, scientific progress has often been marked by unexpected leaps forward, where one discovery opens the door to entirely new fields of research. There is also the possibility of international cooperation speeding up the process. If nations come together to share their resources and knowledge, the development of faster-than-light travel could accelerate significantly. Joint efforts have already proven successful in other areas of space exploration. On the other hand, there are still many unknowns. Challenges in understanding the fundamental laws of physics or the practicalities of manipulating space-time might stall progress for centuries. There is no guarantee that warp travel will be possible within the next few generations or even within the next few hundred years. We also must consider the ethical and societal implications. Even if the technology were to be developed quickly, there would need to be a period of adjustment where society grapples with how to use it responsibly. This could delay the implementation of warp drives by decades or more. Ultimately, the time frame for realizing faster-than-light travel will depend on a combination of scientific discovery, technological innovation, and societal will. While it's impossible to say exactly when it will happen, the journey toward unlocking this extraordinary capability has already begun. One of the biggest challenges in developing warp drive technology is the enormous energy requirement. Reducing this energy demand is essential if faster-than-light travel is ever to become feasible. Scientists are exploring various methods to lower the amount of energy needed to create and sustain a warp bubble. One approach to reducing energy requirements is by altering the shape of the warp bubble itself. Early models of the Alcubierre drive assumed a spherical bubble, but more recent research suggests that a flattened or more elongated bubble could drastically reduce the energy needed to manipulate space-time. Another possibility is using quantum effects to generate the necessary energy. Some researchers are investigating how quantum fields might provide a more efficient way to warp space-time, potentially tapping into the energy fluctuations of the vacuum. This would allow us to use energy more effectively. Improving our understanding of exotic matter is also crucial. If we can discover or produce more stable forms of negative energy or negative mass, it might become easier to create a warp bubble with less energy. This could lead to a significant reduction in the amount of power required. There's also interest in exploring more efficient energy sources. Current proposals depend on massive amounts of conventional energy, but future advances in fusion energy or antimatter could help provide the power needed for faster-than-light travel in a more compact and sustainable way. Tapping into naturally occurring energy in space could be another way to reduce the energy demands of warp technology. For example, some have suggested using the energy of black holes, stars, or dark energy as potential sources. These cosmic phenomena might provide vast amounts of energy without the need for massive infrastructure on Earth. Another theoretical concept is the idea of a warp drive that creates a smaller, localized distortion in space-time. Instead of a large ship-sized bubble, a smaller region of warped space might require far less energy, making short-distance or slower-than-light travel more achievable in the near term. Researchers are also investigating whether energy recycling within the warp bubble could be possible. If the energy used to create the bubble could be continuously cycled or regenerated within the system, it might drastically lower the external energy inputs needed to keep the warp drive operational. Collaboration with material science is another area that could hold the key to reducing energy needs. If new materials can be developed that interact with space-time more efficiently, they might help focus or amplify the energy used to generate a warp bubble, reducing the total power required. Advances in energy storage systems could also help. If we can develop more efficient batteries or energy storage devices, spacecraft may not need to carry as much fuel or generate all the energy they need during flight. This would allow warp drives to operate more efficiently over longer distances. Some theorists believe that breakthroughs in our understanding of space-time itself could reveal shortcuts for reducing energy demands. There may be aspects of the universe's structure we don't yet fully understand that could allow us to manipulate space with far less effort than currently predicted. Ultimately, reducing the energy requirements for warp drives will be critical for their success. The more we learn about space-time, exotic matter, and energy, the closer we will come to making faster-than-light travel a reality with energy demands that are actually achievable. Improving our understanding of exotic matter is crucial to making faster-than-light travel a reality. Exotic matter, particularly negative energy or negative mass, is theorized to be necessary for creating the space-time distortions that enable a warp drive. But so far, this type of matter remains purely theoretical. One challenge in studying exotic matter is that it doesn't behave like the regular matter we interact with every day. Negative mass, if it exists, would move in the opposite direction to any applied force. This counterintuitive behavior makes it difficult to model or predict how it would interact with other forms of matter and energy. Physicists are working to understand if negative energy can be harnessed through quantum effects. The Casimir effect, which shows that vacuum fluctuations between two closely spaced plates can create a small force, is one real-world phenomenon that hints at the possibility of negative energy. But scaling this up to the levels required for warp travel is a major challenge. Another area of research focuses on quantum field theory, which suggests that exotic matter might emerge under extreme conditions, such as near black holes or in the early universe. If we can recreate similar conditions in the lab, we might be able to observe exotic matter or negative energy directly. Some scientists are investigating whether exotic matter could be produced in particle accelerators. By smashing particles together at incredibly high speeds, it might be possible to generate negative energy or create conditions that mimic the behavior of exotic matter. However, we are still far from achieving this goal. If we could develop a deeper understanding of how exotic matter interacts with space-time, it might lead to entirely new approaches to propulsion. We could learn how to create localized pockets of negative energy, which could reduce the energy demands for generating a warp bubble. There is also the possibility that exotic matter exists naturally somewhere in the universe. If we can detect or locate it in space, it could provide a breakthrough in understanding how to harness it for technological purposes. Observing exotic matter in its natural state would offer invaluable insights. Theoretical models of dark energy are another avenue being explored. Dark energy, which is believed to drive the expansion of the universe, may share some properties with exotic matter. If connections between dark energy and negative energy are discovered, it could revolutionize our understanding of both and provide new tools for space-time manipulation. Improving our understanding of exotic matter also requires advances in mathematics and computational models. By refining the equations that describe space-time and energy, physicists hope to better predict how exotic matter could be controlled and utilized for practical applications. Collaboration across disciplines is essential to this research. Quantum physicists, cosmologists, and engineers all have valuable insights that could contribute to understanding exotic matter. Working together, they can address the complex challenges that surround this mysterious form of matter. The search for exotic matter is also driving advancements in experimental physics. New tools, such as more powerful particle accelerators and more sensitive detectors, are being developed to probe the fundamental forces of the universe. These tools might one day reveal the existence of exotic matter. Ultimately, improving our understanding of exotic matter will be key to unlocking the potential of warp drives. The more we learn about how this strange form of matter works, the closer we will come to creating the technologies needed to explore the universe at faster-than-light speeds. Creating stable warp bubbles is one of the most critical challenges in developing faster-than-light travel. A warp bubble would need to form around a spacecraft, compressing space in front and expanding it behind, but ensuring that this bubble remains stable throughout the journey is a monumental task. One of the key issues is controlling the energy within the warp bubble. If the energy fluctuates too much, the bubble could collapse, potentially destroying the spacecraft. Managing this energy with precision is essential to prevent catastrophic failure during travel. The stability of the warp bubble also depends on how space-time itself is manipulated. Even small disturbances in the structure of space-time could disrupt the bubble. Ensuring that the bubble maintains its shape while moving through different regions of space is a significant technical challenge. Another problem is how the bubble interacts with the space outside. If the boundary of the warp bubble interacts too strongly with normal space, it could cause friction or other destabilizing effects. Finding ways to minimize these interactions is crucial for maintaining the integrity of the bubble. Researchers are exploring whether exotic matter, specifically negative energy, could help stabilize the warp bubble. Negative energy is theorized to counteract some of the destabilizing forces that occur when space-time is warped, but producing and controlling enough of it remains a major obstacle. It's also possible that certain configurations of the warp bubble might be more stable than others. By experimenting with different shapes or designs, scientists hope to find a configuration that reduces the risk of instability and allows for smoother travel through warped space. The edges of the warp bubble are another area of concern. The transition between normal space and warped space could create intense forces, and managing these forces is essential to avoid tearing the bubble apart. Developing new materials or technologies to handle these transitions will be important for future designs. Communication within the bubble is another issue that needs to be solved. Current methods of communication rely on signals traveling at the speed of light, but inside a warp bubble, space-time behaves differently. Engineers will need to create new systems that allow for stable communication with the outside world during travel. The bubble's lifespan also poses a challenge. Even if we can create a stable bubble, it needs to last for the entire duration of the journey. Finding ways to maintain the bubble without requiring constant input of enormous amounts of energy is another critical hurdle to overcome. There's also the question of deceleration. When a warp bubble reaches its destination, it needs to collapse in a controlled manner. An unstable collapse could release a massive amount of energy, creating a dangerous situation. Safely transitioning out of the warp bubble is as important as creating it in the first place. Some scientists are experimenting with simulations to better understand how warp bubbles might behave in various conditions. These simulations allow researchers to test different theories and models without needing to create a physical warp bubble, providing valuable insights into the stability problem. Ultimately, creating stable warp bubbles will require breakthroughs in both physics and engineering. It's not just about bending space-time, but doing so in a way that keeps the spacecraft and its occupants safe while moving faster than light. Stability will be the key to making warp travel a practical reality. In addition to the Alcubierre warp drive, there are several alternative theories and models for faster-than-light travel. Each of these concepts approaches the challenge of breaking the light-speed barrier in a different way, offering new possibilities and potential solutions. One alternative is the concept of traversable wormholes. Wormholes are theoretical tunnels through space-time that could connect distant regions of the universe. If we could create a stable wormhole, it might allow for near-instantaneous travel between 2 points, bypassing the need to exceed the speed of light. Another model is based on manipulating the structure of the universe itself. Some physicists have proposed that by controlling the expansion of space, we might be able to create warp corridors that stretch and contract space, allowing a spacecraft to cover large distances without technically moving faster than light. Tachyons are another concept explored in alternative models. These hypothetical particles are theorized to travel faster than light, but their existence has never been proven. If tachyons do exist, they could provide a clue to unlocking faster-than-light travel through new types of propulsion systems. The concept of quantum tunneling also offers an intriguing possibility. In quantum mechanics, particles can sometimes pass through barriers instantaneously. Some researchers wonder if this phenomenon could be scaled up to allow spacecraft to tunnel through space-time, bypassing the light speed limit. The idea of a Krasnikov tube is another alternative. This theoretical structure involves creating a narrow, one-way tunnel in space-time that could allow for faster-than-light travel. It's based on the manipulation of space-time similar to the warp bubble, but would function differently, potentially requiring less energy. Brain theory, an offshoot of string theory, also presents a speculative model. It suggests that our universe is just one of many brains floating in higher dimensional space. If we could somehow navigate between these dimensions, It might provide a shortcut for faster-than-light travel within our own universe. Some researchers are exploring how dark energy, the mysterious force driving the expansion of the universe, might be harnessed for faster-than-light travel. By better understanding how dark energy affects space-time, we might discover ways to manipulate it for propulsion. Quantum entanglement, while primarily focused on communication, has also sparked curiosity about its potential applications for faster-than-light travel. If entangled particles can share information instantly across great distances, some theorize that it could lead to new ways of thinking about space and time. The idea of the warp shell is another variant. This concept focuses on creating a localized bubble around the spacecraft that moves through space differently than the surrounding environment, similar to a warp bubble, but with distinct mechanisms for achieving the distortion. Advanced forms of laser propulsion have also been considered. Some scientists believe that highly focused beams of light, combined with mirrors or reflective sails, might push a spacecraft to near light speeds. While not faster than light, it's seen as a potential stepping stone toward more advanced technologies. While none of these alternative theories have been proven, they offer valuable insight into the diverse approaches being explored. Each model presents its own set of challenges, but together they expand our understanding of what might be possible in the quest for faster-than-light travel. Government and private partnerships will be essential in the development of faster-than-light travel. Both sectors bring unique strengths to the table, and their collaboration could accelerate breakthroughs in warp technology and advanced propulsion systems. Governments, through agencies like NASA or the European Space Agency, have the funding and long-term commitment needed for complex space exploration projects. They can provide the necessary infrastructure for large-scale research, development and testing of new technologies, including warp drives. Private companies, on the other hand, bring innovation and agility. Corporations like SpaceX, Blue Origin and others have shown they can rapidly develop new technologies and push the boundaries of what's possible in space exploration. Their involvement could help drive faster progress by streamlining operations and introducing new ideas. Collaboration between these two sectors could allow for shared resources, where government-funded research programs work alongside private companies to turn theoretical concepts into practical technologies. By pooling expertise and knowledge, both parties could reduce costs and increase the speed of development. Private companies are also well positioned to commercialize faster-than-light travel if it becomes viable. Once the foundational research is completed, private firms can focus on the manufacturing and operational side of warp travel, potentially making interstellar exploration accessible on a much wider scale. Governments, in turn, could provide regulatory frameworks and safety standards to ensure that warp travel is developed responsibly. These partnerships would ensure that ethical considerations, environmental impacts and safety protocols are prioritized as the technology moves forward. Another advantage of public-private partnerships is the potential for shared risk. Developing faster-than-light travel is incredibly risky, both financially and technologically. By working together, governments and private companies can spread that risk, making it easier to secure funding for long-term research. Private sector involvement can also help drive competition. Multiple companies working on similar technologies can lead to rapid advancements, as each strives to outpace the others. This competitive environment could lead to the discovery of new methods for manipulating space-time or reducing energy requirements. Governments can further incentivize private companies by offering grants, subsidies, or contracts to those who are willing to invest in research and development. These financial incentives could attract more companies to the field, broadening the scope of research efforts. International government cooperation could expand the benefits of these partnerships. By bringing together companies and researchers from different countries, public-private collaborations could foster global innovation in faster-than-light travel, ensuring that the technology is developed for the benefit of all humanity. The success of space exploration programs like the International Space Station proves that collaborative efforts between governments and private entities can work. A similar model could be applied to faster-than-light travel, with each partner focusing on its strengths to make the technology a reality. Ultimately, government and private partnerships will be the driving force behind faster-than-light travel. By working together, they can overcome the challenges of cost, risk, and technological development, paving the way for humanity's next great leap into the stars. The concept of the warp drive first gained widespread attention through science fiction, particularly in works like Star Trek. In this universe, warp drive allowed starships to travel faster than light, enabling interstellar exploration and the discovery of new worlds. This idea captivated audiences and inspired generations of scientists and engineers. Star Trek introduced the idea of bending space-time to achieve faster-than-light travel, presenting it as a practical, almost routine technology. While the series didn't delve deeply into the physics, it popularized the notion of space-time manipulation, bringing it into mainstream culture. Isaac Asimov's Foundation series also explored the idea of faster-than-light travel. In his books, spaceships moved through a hyperspace, a separate dimension that allowed for quick jumps between distant points in the universe. This concept of using alternate dimensions for travel became a recurring theme in science fiction. Other early sci-fi writers, such as Arthur C. Clarke and Robert Heinlein, also speculated about faster-than-light travel. Their works often involved advanced alien civilizations, using warp drives or similar technologies to explore the galaxy or communicate across vast distances. The appeal of warp drives in science fiction often stems from their ability to overcome the immense distances between stars. Without this technology, most space exploration stories would be limited to our solar system, reducing the scope for storytelling and adventure. Sci-fi also explored the idea of warp drives as a metaphor for human curiosity and ambition. Faster-than-light travel allowed for stories about exploration, discovery, and the unknown, reflecting humanity's desire to push boundaries and seek out new frontiers. In more recent sci-fi, works like Interstellar and The Expanse have built on these early ideas, using more realistic depictions of space travel, but still imagining ways to overcome the light-speed barrier. These stories often incorporate real scientific theories, blending fiction with cutting-edge concepts in physics. The idea of the warp drive has inspired real scientific inquiry. Scientists like Miguel Alcubierre, who proposed a theoretical model for a warp drive in 1994, have acknowledged the influence of science fiction on their work. Sci-fi provided the imaginative framework that allowed them to think beyond conventional physics. Science fiction continues to shape how we think about faster-than-light travel. New shows, books, and movies explore the potential challenges, risks, and ethical dilemmas of warp technology, keeping the conversation alive in popular culture and scientific communities alike. In these stories, warp drives often symbolize freedom and progress, representing humanity's ability to transcend limits and explore the universe. This sense of boundless opportunity has helped maintain the allure of faster-than-light travel in the public imagination. At the same time, sci-fi also explores the darker sides of warp technology, from its potential for misuse to the unforeseen consequences of tampering with space-time. These cautionary tales remind us that even the most promising technologies come with risks. Ultimately, the origins of warp drive in sci-fi have helped spark serious scientific interest in the concept. What began as a fictional plot device has grown into a legitimate field of study, with researchers now exploring whether the ideas first imagined by writers could one day become reality. When we compare sci-fi technology like warp drives to real physics, the differences are stark, yet they also inspire scientific curiosity. Sci-fi often simplifies complex scientific concepts for storytelling, presenting faster-than-light travel as routine, whereas real physics imposes strict limitations on such possibilities. In Star Trek, warp drives bend space-time to allow faster-than-light travel, but the mechanics are rarely explained in detail. In reality, Einstein's theory of relativity tells us that nothing can travel faster than light in normal space, creating a significant hurdle that sci-fi often ignores or skirts around with fictional technologies. The idea of using hyperspace, as seen in many sci-fi stories, bypasses this limitation by imagining a separate dimension where the laws of physics are different. However, real physics hasn't discovered such a dimension, and there's no evidence that hyperspace, as described in fiction, exists. In fiction, warp drives often run on futuristic energy sources that are never fully explained, making interstellar travel seem effortless. In real physics, the energy required to manipulate space-time, based on current theories, would be astronomical, far beyond anything we can generate with today's technology. Time dilation, a real consequence of traveling near the speed of light, is often ignored in sci-fi. In reality, as you approach light speed, time slows down relative to an outside observer, leading to potential issues with aging and communication that most sci-fi glosses over for the sake of narrative simplicity. Real physics also imposes constraints on causality. Traveling faster than light could, in theory, lead to violations of cause and effect, something that's rarely addressed in science fiction. Sci-fi stories often portray faster-than-light travel as instantaneous, without the paradoxes that might arise from altering the sequence of events. In terms of propulsion, sci-fi often portrays ships using warp cores or hyperspace engines that make interstellar travel look easy. Real-world physics, on the other hand, is still focused on propulsion methods like ion drives or nuclear fusion, which are powerful but nowhere near fast enough for interstellar travel. Sci-fi technologies also assume perfect control over space-time, allowing ships to jump between star systems with precision. In reality, even if we could manipulate space-time, maintaining stability and control over a warp bubble or wormhole would be a huge technical challenge that science is far from solving. Exotic matter, which is often used in sci-fi as the key to warp drives, remains purely theoretical in real physics. While science fiction suggests it's readily available for use in starships, physicists have yet to prove its existence or figure out how to harness it for practical applications. Quantum mechanics, often cited in sci-fi as a way to explain faster-than-light communication or travel, does allow for strange phenomena like entanglement, but these don't currently offer any clear path toward breaking the light-speed barrier in real-world physics. Despite these differences, sci-fi has played a crucial role in inspiring real scientific inquiry. Many physicists today were motivated by the possibilities they saw in stories like Star Trek or Dune. While the science in these stories is often speculative, it has sparked ideas that drive research into warp drives, wormholes, and advanced propulsion. Ultimately, comparing sci-fi technology to real physics reveals both the gaps in our current understanding and the potential for future breakthroughs. While many of the ideas in science fiction remain beyond our reach, they challenge scientists to push the boundaries of what's possible, slowly bringing fantasy closer to reality. Many popular misconceptions about warp travel stem from its portrayal in science fiction. One of the most common is the idea that warp drives simply allow ships to travel faster than light, in the same way a car moves down a road. In reality, a warp drive would manipulate space itself, creating a bubble where space-time expands and contracts around the ship. Another misconception is that faster-than-light travel would feel instantaneous to the people on board. Sci-fi often skips over the fact that time dilation or other relativistic effects might still play a role, even with a warp drive. The experience of time could be very different from what we see in fictional depictions. People also assume that a warp drive would make long-distance space travel simple and routine, like a quick jump between planets. However, the energy required for such a drive, based on current theoretical models, would be immense, far more than what any spaceship could generate with today's technology. There's also the idea that warp travel can be done without consequences. In reality, manipulating space-time on such a large scale could have unforeseen effects, potentially damaging the space around the warp bubble or creating dangerous conditions at the ship's destination. Some believe that once warp technology is developed, it will instantly open the door to the entire universe. In fact, even if warp travel becomes possible, it might still take a significant amount of time to reach other star systems, depending on how the technology is used and what limitations it has. Another common misconception is that the laws of physics would no longer apply during warp travel. While warp drives work around the light speed limit imposed by Einstein's relativity, they wouldn't violate physics, but rather use the principles of general relativity to bend space itself. Sci-fi often presents the idea that warp drives could be used repeatedly without issue. However, in reality, every warp jump could carry significant risks, from energy depletion to the collapse of the warp bubble, making each journey a calculated risk rather than a routine mission. People sometimes confuse warp travel with wormholes or hyperspace travel, assuming all faster-than-light methods are the same. While both involve faster-than-light concepts, they operate on different theoretical principles, with wormholes focusing on shortcuts through space-time and warp drives on bending space around the ship. There's also a misconception that warp travel would allow ships to zip around galaxies without interacting with the space in between. In reality, the ship would still need to navigate through interstellar space, and potential hazards like cosmic radiation or debris would need to be accounted for. Some people believe that warp travel, once achieved, will eliminate the need for other propulsion technologies. But even with warp drives, traditional propulsion systems would likely still be required for navigating within star systems or making smaller maneuvers. A common misunderstanding is that creating a warp bubble would be simple once the theory is proven. In fact, the technical challenges of generating and maintaining a stable warp bubble are enormous, requiring advancements in energy production, material science, and space-time manipulation far beyond our current capabilities. Finally, many assume that warp travel, like in the movies, would be affordable and accessible to everyone. In reality, the development of such technology would likely be incredibly expensive, and even if it becomes possible, it might take decades or centuries before it is widespread or cost-effective for civilian use. Science fiction has long been a driving force behind scientific innovation, sparking curiosity and inspiring generations of scientists to push the boundaries of what's possible. Concepts like warp drives, teleportation, and artificial intelligence, once confined to the pages of novels and the screens of movies, have motivated real-world research into advanced technologies. Sci-fi doesn't just present futuristic ideas, it frames them in a way that captures the imagination. By imagining scenarios where humanity explores distant stars or interacts with advanced alien species, it encourages scientists to think creatively about how we might achieve these feats in reality. The depiction of advanced propulsion systems in sci-fi, such as the warp drives in Star Trek, has led physicists to consider the theoretical underpinnings of faster-than-light travel. The idea that space itself could be manipulated has been explored in serious academic papers, inspired by what was first introduced in fiction. Artificial intelligence is another area where science fiction has had a major impact. Stories about sentient robots or powerful computers have encouraged scientists to delve deeper into machine learning and AI. Today, these concepts are no longer just fiction, but a significant field of study, transforming industries and societies. Medical advancements have also been influenced by sci-fi. The idea of handheld medical scanners, for example, has inspired the development of modern diagnostic tools. Concepts like gene editing and personalized medicine, now in their early stages, were once purely speculative ideas in science fiction. Space exploration, perhaps more than any other field, has been directly shaped by sci-fi narratives. The vision of exploring new worlds and establishing colonies on distant planets continues to fuel interest in space programs and private ventures. The idea of space travel as a common experience started with fiction, but is gradually moving toward reality. Sci-fi often raises questions about ethics and responsibility, prompting real-world discussions on how emerging technologies should be used. As we develop more advanced AI, robotics, and even the possibility of altering human genetics, sci-fi stories provide a framework for debating these issues before they become real dilemmas. The collaborative nature of sci-fi and science is another key factor. Writers often draw on current scientific knowledge to make their stories believable, and in turn, scientists take inspiration from those stories, pushing the boundaries of technology to match what they've seen in fiction. Sci-fi has also encouraged scientific progress by normalizing the idea of exploration and risk-taking. Stories of brave explorers venturing into the unknown inspire real scientists and engineers to take calculated risks in pursuit of groundbreaking discoveries, whether it's launching a new mission to Mars or developing a revolutionary energy source. Public interest in scientific research is often driven by science fiction as well. Sci-fi movies and books captivate wide audiences, making complex scientific concepts more accessible and sparking interest in fields like astrophysics, quantum mechanics, and robotics among the general public. Through speculative technologies, sci-fi fosters a sense of possibility. It pushes us to ask what if, and then challenges the scientific community to explore whether those ideas can be made real. Many modern technologies, from smartphones to virtual reality, were once seen only in science fiction, showing how these imaginative works can predict and guide future innovation. Ultimately, the role of science fiction in inspiring scientific innovation is undeniable. It acts as a bridge between imagination and reality, providing both the dreams and the motivation needed to turn the impossible into the possible. The cycle of inspiration continues as new technologies emerge, sparking the next generation of science fiction and scientific exploration. Science fiction has provided countless examples of technologies that seemed far-fetched at the time, but have since become reality. One of the most famous examples is the mobile phone. Early versions of mobile communication devices, like the communicator from Star Trek, are now a common part of daily life, evolving into smartphones that go beyond what sci-fi once imagined. The idea of artificial intelligence, once confined to the realm of fiction, is now a rapidly growing field. Stories of thinking machines like HAL 9000 in 2001: A Space Odyssey laid the groundwork for our current exploration of AI, with advancements in machine learning, automation, and neural networks becoming more sophisticated every year. Space travel itself was once considered science fiction. Jules Verne's From the Earth to the Moon was one of the earliest depictions of humans journeying into space. Today, space agencies like NASA and private companies like SpaceX have made space travel a reality, with missions to the Moon, Mars, and beyond becoming a serious focus. Self-driving cars, a staple of futuristic cities in films and novels, are now being developed by major tech companies and car manufacturers. Autonomous vehicles, once purely speculative, are on the verge of becoming a common feature on our roads, with significant advancements in AI and sensor technology driving this innovation. The concept of virtual reality, seen in sci-fi works like The Matrix or Ready Player One, is now being realized with modern VR headsets and immersive environments. While we're not yet living in fully simulated worlds, VR is making significant strides in gaming, training, education, and even social interaction. Medical technology has also been shaped by science fiction. Devices like the tricorder from Star Trek, which could diagnose illnesses on the spot, have inspired the creation of portable diagnostic tools. Today, handheld devices can monitor vital signs, blood sugar levels, and even perform ultrasound scans, bringing us closer to the vision presented in sci-fi. Drones, often depicted in futuristic sci-fi worlds as tools for surveillance or delivery, are now widely used in real life. From military applications to commercial uses like package delivery and aerial photography, drones have become a reality that mirrors their fictional counterparts. Robotics is another area where science fiction has anticipated the future. Autonomous robots, once imagined as humanoid companions or laborers, are now a vital part of industries ranging from manufacturing to healthcare. Robots like Boston Dynamics creations show just how far we've come in turning sci-fi robots into reality. In the field of medicine, bionic limbs and prosthetics that enhance human abilities were once the stuff of sci-fi fantasy. Today, advancements in biotechnology and robotics are making it possible to create artificial limbs that respond to neural signals, giving people a level of control over their prosthetics that was once unimaginable. Space stations, depicted in films like 2001: A Space Odyssey, have become a reality with the International Space Station, where astronauts live and work for extended periods. This permanent human presence in space has paved the way for future exploration and potential colonies on other planets. Quantum computing, often referenced in sci-fi as the next leap in computational power, is now in development. Companies like IBM and Google are making breakthroughs in this field, with quantum computers holding the potential to solve problems far beyond the capacity of today's machines. Even the dream of 3D printing, where objects are created layer by layer, has moved from science fiction to reality. Today, 3D printing is used in everything from manufacturing to medicine, with the potential to create complex structures, including organs, revolutionizing industries, and reshaping how we build and create. Wormholes, also known as Einstein-Rosen bridges, are one of the most intriguing concepts in both science fiction and theoretical physics. They represent hypothetical tunnels through space-time, connecting two distant points in the universe. If they exist, they could allow for instantaneous travel across vast cosmic distances. The idea of wormholes comes directly from Einstein's theory of general relativity. In 1935, Einstein and his colleague Nathan Rosen proposed the concept of a bridge between 2 points in spacetime, which later became known as the Einstein-Rosen bridge. This mathematical solution suggests that space-time could fold in on itself, creating a shortcut between distant regions. In theory, a wormhole could allow for faster-than-light travel without violating the laws of physics. Instead of moving through space at incredible speeds, a spacecraft could enter one end of the wormhole and emerge on the other side, having traveled an immense distance almost instantly. However, while wormholes are possible solutions within the framework of general relativity, there's no experimental evidence that they actually exist. They remain purely theoretical, and the conditions required to create or stabilize a wormhole are far beyond our current technological capabilities. One of the biggest challenges with wormholes is their inherent instability. Without exotic matter, matter with negative energy density, a wormhole would likely collapse before anything could pass through it. This exotic matter would be required to keep the tunnel open, but we have yet to discover how to produce or control such matter. Theoretical physicists also question whether a traversable wormhole could be made large enough for humans or spacecraft to pass through. The energy needed to create a stable, large-scale wormhole would be astronomical, raising doubts about whether this could ever be achieved in practice. In addition to stability issues, wormholes could also pose significant risks. The intense gravitational forces near the entrance or exit of a wormhole could potentially rip apart any matter that approaches it. Navigating these forces would require technology far more advanced than anything we have today. Time travel is another fascinating aspect of wormholes. Some theories suggest that a wormhole could allow for not only travel across space, but also across time. This raises complex questions about causality and paradoxes, such as the grandfather paradox, where an event in the past could be altered by actions in the future. Even if wormholes exist, their entrances might be hidden deep within black holes, which themselves are dangerous and difficult to explore. Some scientists theorize that the center of a black hole could contain a wormhole, but getting close enough to find out would involve overcoming intense gravitational forces. Wormholes are often depicted in science fiction as stable gateways between planets, star systems, or even dimensions. Movies like Interstellar and shows like Stargate have popularized the idea of wormholes as a convenient form of space travel, though these representations are often more optimistic than the science currently supports. Despite the many challenges, research into wormholes continues to push the boundaries of theoretical physics. Even if practical wormhole travel remains far off, studying them helps scientists better understand the fabric of space-time and the extreme conditions that exist in our universe. The search for a real, traversable wormhole may remain a distant goal, but the concept continues to inspire both scientists and science fiction writers. Weather. Hyperspace travel is one of the most popular concepts in science fiction, offering a way for ships to traverse vast distances faster than light by entering a separate dimension. In many stories, hyperspace functions as a parallel realm where the normal laws of physics don't apply, allowing ships to move between distant points in space quickly. One of the most famous depictions of hyperspace is in Star Wars. In this universe, starships use hyperdrives to jump into hyperspace, effectively bypassing the slow travel through normal space. This idea allows for galactic empires and civilizations to exist, with travel between planets happening in a matter of hours or days. In Babylon 5, hyperspace is shown as a separate dimension full of energy and turbulence. Ships travel through hyperspace using beacons to navigate, but it's a dangerous place where one could easily become lost if not careful. This adds a sense of peril to the otherwise fast method of travel. Stargate introduced the idea of hyperspace in a slightly different way. The show's wormhole travel used stargates to link distant worlds, but ships could also use hyperspace as a faster-than-light method to move between star systems. This reinforced the idea that hyperspace was an efficient, if risky, way to explore the galaxy. In The Expanse, while the series remains grounded in more realistic physics, there are still discussions of advanced propulsion systems that hint at concepts inspired by hyperspace. These ships move quickly across the solar system, suggesting that while hyperspace isn't directly mentioned, faster-than-light travel remains a distant possibility. Hyperspace in fiction is often portrayed as an invisible or alternate dimension, with few rules compared to normal space. This creative liberty allows writers to bypass the constraints of light-speed travel, making interstellar civilizations feasible. However, in reality, no evidence supports the existence of such a dimension. Despite being a fictional construct, hyperspace has captured the imagination of scientists and audiences alike. The idea of slipping into another realm to avoid the limitations of our own universe is fascinating, even if it defies what we currently understand about physics. Hyperspace also plays into the concept of shortcuts through space. In many stories, hyperspace is not just faster, but fundamentally different, where distances in normal space are compressed or bypassed entirely. This makes interstellar travel possible on a scale that traditional propulsion methods would never allow. In Warhammer 40,000, hyperspace is referred to as the warp, a dangerous and unpredictable realm inhabited by malevolent entities. This version of hyperspace introduces the idea of a supernatural or chaotic element, where space travel isn't just scientific but also metaphysical, reflecting the high stakes of faster-than-light journeys. Other stories, like Farscape, depict hyperspace as more of a natural phenomenon that ships can tap into, using advanced technology to open a gateway into this faster realm. These variations show how flexible the concept of hyperspace can be, adapting to different storytelling needs across genres. Some sci-fi writers use hyperspace as a way to explore the philosophical implications of faster-than-light travel. In these stories, entering hyperspace might affect the passage of time, the nature of reality, or even the traveler's perception of the universe. This adds a layer of depth to what is often portrayed as a purely mechanical process. Though hyperspace remains fictional, its appeal lies in the possibilities it presents. It offers a tantalizing solution to the vast distances between stars, allowing for stories of exploration, conflict, and discovery to unfold on a galactic scale without the faster-than-light communication has fascinated scientists and storytellers alike, as it offers the possibility of instant communication across vast distances. One of the most well-known theories involves quantum entanglement, where two particles are connected in such a way that the state of one instantly affects the state of the other, no matter the distance between them. In theory, quantum entanglement could be used to send information instantly, but in practice it doesn't seem to allow for faster-than-light messaging. Although the particles are entangled, the act of measuring one does not transmit useful information faster than light, meaning it can't yet be used for communication. Another theory is based on hypothetical tachyons, particles that always travel faster than light. If tachyons exist, they might carry signals across great distances almost instantaneously. However, tachyons remain speculative, and their existence has yet to be proven. Sci-fi often portrays faster-than-light communication as commonplace, but in reality the speed of light is a fundamental limit in relativity. Signals, whether they're radio waves or light, must adhere to this limit, making real-time communication over light years currently impossible. The idea of using wormholes for communication has also been proposed. In this model, a wormhole could link 2 points in space-time, allowing a message to travel instantly through the tunnel. While theoretically possible, no evidence of stable, traversable wormholes has been found. In some fictional universes, hyperspace plays a role in faster-than-light communication. Just as ships can travel through hyperspace, signals might also use this alternate dimension to bypass the speed of light. This concept is purely speculative, with no basis in current scientific understanding. There are also speculative ideas involving the manipulation of space-time itself. If space can be warped to allow faster-than-light travel, then in theory, the same principle could apply to communication. This would involve bending or compressing space to shorten the distance a signal must travel. Some scientists are exploring the possibility of using neutrinos for communication. Neutrinos are subatomic particles that pass through matter with little resistance, and while they still travel below the speed of light, they might one day enable communication across extreme distances with far less interference than conventional signals. The challenge of faster-than-light communication also involves time. If information could be transmitted faster than light, it could, in theory, lead to paradoxes where the effect occurs before the cause. This breaks the laws of causality, which is a fundamental concept in both physics and our understanding of the universe. Another issue is energy. Even if faster-than-light communication were theoretically possible, the energy required to send signals instantaneously across light years could be immense, raising questions about whether such technology could ever be practical or sustainable. Despite the challenges, the pursuit of faster-than-light communication continues to inspire research. While we haven't yet found a way to break the light-speed barrier, advances in quantum mechanics, theoretical physics, and space-time manipulation could one day offer new insights. For now, faster-than-light communication remains in the realm of speculation and science fiction. But like many other futuristic technologies, it continues to drive innovation and curiosity, pushing the boundaries of what we know and challenging scientists to explore new possibilities. Quantum entanglement is one of the most intriguing phenomena in quantum mechanics. It occurs when two particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This strange connection has sparked interest in its potential applications, especially in communication. Entanglement seems to defy the limitations of distance. When one entangled particle is measured, the other particle, even if it's on the opposite side of the universe, will reflect that change instantly. This has led to speculation that quantum entanglement might hold the key to faster-than-light communication. However, while entanglement allows for this instant correlation between particles, it doesn't transmit information in a way that can be used for communication. The results of the measurement are random, and the instant link between the particles can't be controlled to send specific messages. Still, quantum entanglement has real-world applications in fields like cryptography. Quantum key distribution uses entanglement to create secure communication channels. If anyone tries to intercept the message, the entangled particles would reflect the interference, alerting the intended users. Entanglement also plays a key role in the development of quantum computers. These computers use entangled particles to process complex information far faster than classical computers. While this won't result in faster-than-light communication, it does open the door to solving problems at unprecedented speeds. There are also hopes that understanding quantum entanglement better could one day reveal new physics. If we can unlock the deeper mysteries of how and why particles remain connected over vast distances, it might offer insights into the fabric of the universe and the potential for new technologies. Some researchers are exploring whether quantum entanglement could be linked with space-time manipulation. If entanglement interacts with space-time in a meaningful way, it could lead to the development of technologies that go beyond our current understanding, though this remains speculative. Entanglement could revolutionize how we think about networks and the transmission of data. Quantum networks, which use entangled particles, could one day allow for instantaneous data transfer over large distances, though this wouldn't necessarily break the speed of light. Another exciting possibility is the use of quantum entanglement in teleportation. While we can't transport matter itself, researchers have successfully teleported the quantum state of particles over distances, an achievement that could eventually lead to advanced forms of data transmission or quantum state replication. As quantum research progresses, the possibilities for entanglement may expand. We are still in the early stages of understanding how to harness this phenomenon fully, but breakthroughs in quantum mechanics could pave the way for entirely new ways of computing, communicating, and interacting with the world. Quantum entanglement also forces us to rethink the nature of reality. The fact that two particles can remain connected across vast distances suggests that the universe might be more interconnected than previously thought. This could lead to philosophical as well as scientific shifts in how we view the world. In the end, while quantum entanglement may not provide faster-than-light communication as once hoped, its potential in other areas remains vast. As research continues, we may find even more surprising ways to utilize this strange and powerful phenomenon. Warp drives remain the best candidate for faster-than-light travel, because they offer a theoretical solution that works within the framework of Einstein's general relativity. Unlike other speculative ideas, warp drives focus on bending space-time itself, rather than trying to break the universal speed limit of light. The key advantage of a warp drive is that it doesn't actually move the ship faster than light through space. Instead, it compresses space in front of the ship and expands it behind, allowing the spacecraft to effectively ride a wave of distorted space-time, bypassing the restrictions imposed by relativity. Another reason warp drives are favored is that the concept has a solid foundation in known physics. The Alcubierre drive, proposed in 1994, uses equations that stem directly from Einstein's theory of relativity, making it a more scientifically grounded idea than concepts like wormholes or hyperspace. Unlike wormholes, which are unstable and speculative, warp drives don't require shortcuts through space-time but manipulate the space around a ship. This makes the idea more feasible, at least in theory, as it doesn't rely on the existence of separate dimensions or hidden portals. While the energy requirements for a warp drive are still immense, advancements in energy research, such as fusion power or antimatter, could one day make it possible to generate the necessary power. Other concepts, like wormholes, may demand even more exotic and unproven technologies. Warp drives also offer a more stable solution for long-term space travel. Once a warp bubble is created, it's theorized that the ship inside would be protected from the relativistic effects of near-light-speed travel, such as time dilation, making warp drives more practical for human space exploration. Exotic matter necessary for creating the negative energy required for a warp drive remains elusive, but it's still a better candidate than the speculative particles needed for some other faster-than-light proposals. At least theoretically, physicists have a direction to explore in order to make warp technology possible. Additionally, warp drives present fewer risks to causality compared to concepts like time travel through wormholes. Since the ship within the warp bubble never exceeds the speed of light locally, it avoids the paradoxes that might arise with other faster-than-light methods that involve altering timelines. Warp drives also have the potential to be more scalable. While other faster-than-light travel concepts often focus on small individual particles or theoretical objects, a warp drive could, in theory, transport entire ships, making it practical for large-scale exploration or colonization efforts. Furthermore, warp drives avoid many of the hazards associated with high-speed travel through normal space, such as collisions with space debris or exposure to radiation. Since the ship is within its own bubble of space-time, it's protected from external threats in a way that more traditional propulsion methods might not be. While we are far from building a working warp drive, the concept continues to inspire both scientific and popular interest. Its combination of theoretical soundness and long-term potential makes it the best candidate for future faster-than-light travel, even if the challenges are immense. As research progresses, warp drives remain the most promising option because they fit within the laws of physics as we currently understand them, while still offering a revolutionary way to explore the cosmos. With enough breakthroughs, warp technology could one day turn interstellar travel from fiction into fact. In this video, we explored the fascinating concept of warp drives and the possibility of faster-than-light travel. We began by discussing the basic concept of faster-than-light travel, looking at why it has been such a dream for humanity and why conventional physics tells us it's not possible through traditional means. From there, we dove into Einstein's theory of relativity, which sets the light-speed barrier but also opens up the possibility of bending space-time itself. We then broke down how the space-time continuum works, explaining how it might be manipulated to allow travel that bypasses the light-speed limit without actually violating the laws of physics. This led us into an examination of energy requirements for warp travel, which, while currently astronomical, may one day be achievable with future advancements in technology. We also covered the theoretical constraints of faster-than-light travel, including the challenges that arise when trying to reconcile it with our current understanding of physics. Miguel Alcubierre's 1994 paper introduced the first real theoretical model for a warp drive, which inspired much of the scientific community's current thinking on the topic. Next, we explored how the warp bubble works, including the mechanics behind compressing space ahead of a spacecraft and expanding it behind. This led us to discuss the energy required for the Alcubierre warp drive and the significant challenges in applying the model in practical terms with today's technology. We talked about the role of exotic matter and negative energy, which are essential components for making warp drives a reality, though both remain elusive in current scientific research. Along the way, we touched on the Casimir effect, quantum fluctuations, and the experimental evidence for negative energy, each of which could provide clues for future breakthroughs. As we ventured into the realm of quantum mechanics, we discussed the potential role of quantum entanglement and other quantum phenomena in understanding space-time manipulation. We highlighted how scientific research is already working on concepts that once seemed like pure science fiction. Throughout the video, we also examined the differences between science fiction and real-world physics, Sci-fi has been instrumental in inspiring innovation and research, but there are many misconceptions about how warp drives and faster-than-light travel would actually work. Finally, we explored some alternative theories, from wormholes to hyperspace, and compared them to the warp drive model, explaining why the latter remains the best candidate for future faster-than-light travel. Government and private partnerships will be essential in making this technology a reality, pushing us toward a new era of space exploration. If you enjoyed this deep dive into warp drives and faster-than-light travel, please give the video a thumbs up and consider subscribing to the channel for more exciting content. Don't forget to check out our other videos covering a wide range of topics related to space, science, and technology. Thank you for watching, and we look forward to seeing you in the next video.